Hello and welcome to Sleepy Science. Tonight, we are going to follow the universe from its first hidden traces to its final quiet darkness. Not as a story of explosions and noise, but as a slow, strange journey through invisible matter, ancient light, dying stars, black holes, expanding space, and questions so large they make everyday life feel almost unreal. Most of the universe is not visible to our eyes. Most of its history happened before us, and much of its future may unfold in silence long after the last stars fade. But for a little while, we live in the bright middle, able to look up, measure the darkness, and ask what kind of reality made all of this possible. Before we begin, let me know in the comments where you are watching from and what time it is there right now. And if you enjoy calm, mind-opening science like this, please like the video. It helps the channel grow and tells me you want more deep journeys through the universe. Why most of the universe is missing from our eyes? What if the universe is not hiding from us, but our eyes are simply too small a doorway to let most of it in? You look into the night and think you are seeing space, yet your vision only catches a thin band of what reality is allowed to send as visible light. Stars appear because they burn. Galaxies appear because billions of stars gather into glowing islands. Nebulae appear because gas is lit, heated, or shaped by nearby radiation. But the universe is not made only of things that glow. A cold planet drifting far from any star would be almost invisible to your naked eyes. A cloud of gas too faint or too cold might pass through the darkness without leaving a beautiful image. Even black holes, unless surrounded by hot falling matter, remain unseen directly because they give no light back. And beyond all of that lies the deeper lesson. Most of the universe's structure is discovered not by sight, but by consequence. We know something unseen surrounds galaxies because their stars move as if more gravity is present than visible matter can provide. We know distant space behaves strangely because the expansion of the universe appears to be speeding up, not slowing down, as simple expectation might suggest. This does not mean scientists are inventing invisible things for drama. It means the universe is teaching through effects instead of appearances. A footprint can reveal an animal without showing its face. A tide can reveal the moon's pull without the ocean ever touching it. In the same way, the cosmos reveals hidden layers through motion, bending light, temperature patterns, and the way galaxies gather across enormous distances. Your eyes, beautiful as they are, were built for sunrise, faces, fire, danger, and the colors of Earth, not for reading the full machinery of existence. So the visible universe is not a lie, but it is incomplete. It is the illuminated edge of something much larger, a soft glow around a reality that does not need to shine to be real. And maybe that is what makes this fact so quietly powerful. It asks you to stop confusing visibility with truth. The sky is not empty where it looks dark. It is not simple where it looks silent. It is not fully known just because it can be photographed. Most of the universe is missing from our eyes because reality was never designed around human sight. We had to build instruments, equations, detectors, and patient questions just to begin hearing what darkness was saying. And when you understand that, the night no longer feels like a black curtain with stars pinned to it. It becomes a reminder that the most important things may not announce themselves with brightness. Some truths shape everything from behind the visible world, quietly holding galaxies, stretching distances, and humbling the mind that tries to see it all. So when you look upward, remember this: you are not staring at nothing. You are staring at the limit of your own senses, and beyond that limit, the universe continues, vast, hidden, and still teaching. Why the night sky is not really empty. The darkness above you is crowded with things too quiet, too thin, or too ancient for your eyes to recognize. When you look between the stars, that black space may seem like emptiness, as if the universe is mostly a silent gap with a few bright fires scattered through it. But the night sky is not truly empty. It is filled with faint gas, drifting dust, old light, charged particles, magnetic fields, frozen fragments, and radiation moving through the deep spaces between worlds. The space between stars is called interstellar space, but it is not a perfect vacuum. It is thinner than anything we can create naturally on Earth. Yet even there, atoms of hydrogen float like invisible grains in an enormous dark room. In some places, these atoms gather into huge clouds, so vast that they can later become nurseries for new stars. In other places, dust made from the remains of older stars drifts through the galaxy, blocking or reddening starlight, quietly changing what telescopes can see. And there is light there too, even where your eyes see none. Radio waves pass through the sky. Infrared glow leaks from cold dust. X-rays flash from violent regions near collapsed stars. The afterglow of the early universe, known as the cosmic microwave background, still washes through all of space like a faded warmth from the universe's first bright age. Even your body is being crossed every second by tiny particles called neutrinos, most of them passing through you and the entire Earth as if both were almost transparent. This is the strange truth. Emptiness in space does not mean nothingness. It means subtlety. It means the universe has lowered its voice below the range of human sight. The black parts of the sky are not blank walls. They are deep reservoirs of matter and energy, spread so thinly that your senses cannot gather them into a picture. And this changes the way you understand silence. A quiet room can still hold air, warmth, memory, and breath. A dark ocean can still be full of life beneath its surface. In the same way, the night sky hides activity inside stillness. Stars are forming in cold clouds. Old starlight is traveling for thousands or millions of years. Dust from dead suns is drifting toward future planets. Invisible fields are guiding charged particles across distances too large for the mind to hold. So when the sky looks empty, it is not because nothing is there. It is because the universe is often too delicate to be seen directly. It teaches through traces, through faint signals, through the patient work of instruments that can listen beyond the eye. And maybe that is why the night feels so peaceful and so overwhelming at once. You are not looking into a void. You are looking into a living darkness, a vast and quiet medium where the remains of ancient stars, the seeds of future stars, and the oldest light in existence all share the same silence. The sky is not empty. It is simply speaking in a language your eyes were never meant to hear. And the more you learn that language, the more the darkness begins to feel full. How the universe can be expanding into nothing. The universe does not need a room outside itself in order to grow. That is the strange idea hiding behind the question of how everything can be expanding into nothing. In everyday life, expansion always seems to require an outside. Smoke spreads into air, water fills a bowl, a balloon pushes into the space around it. So when you hear that the universe is expanding, your mind naturally asks, expanding into what? But space is not an object sitting inside a larger container. In modern cosmology, space itself is the thing whose distances can change. Galaxies are not mostly racing through a pre-existing darkness like sparks flying from an explosion. Instead, on the largest scales, the space between faraway galaxies is stretching, so the distance between them grows even when they are not moving through space in the ordinary sense. A useful way to feel this is to think of marks drawn on the surface of a stretching sheet. The marks do not need to crawl across the sheet for the distance between them to increase. The sheet itself changes, and the separation grows from within. The universe is similar, though deeper, because it is not expanding into a higher empty room that we can point to. The expansion is a change in the geometry of the universe itself, a widening of the stage rather than actors running toward the walls. This also means there may be no outer edge where space suddenly meets a border, no cosmic cliff where the universe ends and a larger emptiness begins. The question, what is outside the universe? May be like asking, what is north of the North Pole? It sounds meaningful because of ordinary language, but it may not describe a real direction within the system we live in. And this is where the idea becomes quietly humbling. Your mind evolved to understand cups, rooms, roads, and horizons. But the universe does not have to obey the shapes your intuition prefers. It can grow without entering anything. It can become more spread out without pushing into a surrounding void. It can carry galaxies farther apart, while small-bound systems, planets, solar systems, galaxies themselves, remain held together by gravity and other forces. So the expansion of the universe is not a wind pulling your body apart, and it is not a blast moving through a black background. It is a slow, large-scale change in the distances between the greatest cosmic structures. The emptiness it expands into is not a place waiting outside. It is more honest to say the universe is not expanding into anything we know. It is simply expanding, and perhaps that is the most unsettling part. Some questions feel impossible, not because the answer is hidden, but because the question was built from the wrong kind of experience. You stand on Earth, inside rooms, under ceilings, and you expect reality to have an outside. But the cosmos may be teaching you that not everything needs a container. Some things are not inside something else. Some things are the setting in which inside and outside begin to have meaning at all. So when you hear that the universe is expanding into nothing, do not picture a glowing sphere swelling into a dark ocean. Picture distance itself becoming more generous. Picture the map changing while every traveler still believes they are standing still. And in that quiet widening, you can feel the mind loosen its grip on familiar shapes, accepting that the universe is not merely large. It is large in a way that changes what largeness means. Why some galaxies are moving away faster than light. Some galaxies are not breaking the speed of light. They are being carried away by a universe whose distances are growing faster than your intuition can follow. At first, this sounds impossible, because you may have heard that nothing can move faster than light. And that rule is real, but it has a very specific meaning. Nothing can race through its local region of space faster than light. A spaceship cannot simply accelerate past light speed. A beam of light still wins every local race. But distant galaxies are not always speeding through space like objects flying away after an explosion. Instead, the distance between us and them can increase because the universe's large-scale structure is expanding. The farther a galaxy is, the more expanding space lies between it and us, and all those growing distances add up. So a very distant galaxy can appear to recede from us faster than light, not because it is locally outrunning light, but because the space between here and there is increasing so quickly. This is one of the most important distinctions in cosmology, because it shows how easily everyday thinking can fail when applied to the whole universe. You are used to motion as something that happens across a fixed background. A car on a road, a bird through air, a stone across water. But on cosmic scales, the background itself participates. The road is not just something traveled, it is part of the change. And this has a haunting consequence. Some galaxies are so far away, and the expansion between us and them is so strong that light they emit today may never reach us. Not because the light is weak, and not because it gives up, but because the distance it must cross grows faster than the light can close it. This does not make the speed of light false. It reveals that the universe is stranger than a simple race. Light is still moving at its ultimate speed through every small region it passes, but the total distance ahead of it can keep stretching. In a quiet way, this means the cosmos is not only expanding, it is also slowly separating regions from one another in terms of future contact. There are galaxies whose ancient light we can still see now, while their present light may already be beyond our future reach. You are looking at them not as neighbors you could ever visit, but as messages from a connection that is gradually fading. And this turns the night sky into something more emotional than a map. It becomes a record of relationships that may not last forever. The universe allows us to see deep into its past, but it does not promise that every part of itself will remain reachable. So when you hear that some galaxies are moving away faster than light, do not imagine them committing a cosmic crime. Imagine instead that reality has two kinds of motion: the motion of things through space and the growth of space between things. One has a speed limit. The other can make distances swell beyond what light can overcome. And in that difference, you learn something profound. The universe is not simply a place filled with objects. It is an evolving fabric of separation, memory, and fading contact. Every distant galaxy is not just far away. It is part of a cosmic story where distance itself can become destiny. The strange limit of the observable universe. There is a border around everything you can ever see, and it is not made of stone, darkness, or distance alone, but of time itself. This is the strange limit of the observable universe, not the edge of all existence, not a wall where reality stops, but the farthest region from which light has had enough time to reach us since the universe became transparent. The universe is about 13.8 billion years old, so it may sound simple to think we can only see 13.8 billion light years away, but the truth is more subtle and far more beautiful. While ancient light was traveling toward us, space was also stretching, so the places that release that light are now much farther away than the travel time alone would suggest. That is why the observable universe reaches tens of billions of light years in every direction, even though the light we receive has not been traveling for that full present-day distance. You are not seeing where those ancient regions are now. You are seeing where their light began its long journey when the universe was younger, denser, and less familiar. This makes the observable universe less like a physical bubble floating in space, and more like a horizon built from history. Just as the ocean horizon does not mean the sea ends, the cosmic horizon does not mean the universe ends. It only marks the limit of what light has been able to tell us so far. Beyond it, there may be more galaxies, more stars, more vast structures, perhaps an amount of universe so large that our visible portion is only a small local patch. But those regions are hidden from us, not necessarily because they are empty, but because their messages have not arrived, and in some cases may never arrive. This is one of the deepest lessons astronomy gives. Seeing is not the same as possessing the whole truth. We live inside a sphere of information, a region defined by what the speed of light and cosmic history allow us to know. Every telescope, no matter how powerful, is still bound by this ancient limit. It can gather fainter light, sharpen details, and look deeper into the past, but it cannot force a signal to arrive before time permits it. And that means the observable universe is both enormous and incomplete. It is the greatest map we can draw, yet it may not be the full territory. Somewhere beyond the reach of all possible sight, there may be galaxies whose light has never touched any human-made instrument, whose stars burn without ever becoming part of our sky. This does not make them unreal. It only means reality can be larger than evidence can directly show. And perhaps that is what makes the cosmic horizon so haunting. It reminds you that knowledge has a shoreline. We can stand there, measure it, name it, build observatories along it, and still understand that something may continue beyond. The universe gives us a visible story, but not necessarily the whole book. So when you think of the observable universe, do not picture the end of space. Picture the edge of cosmic memory, the farthest glow that has managed to reach our small planet after billions of years of travel. It is not a prison, but a boundary of knowing. And beyond that boundary, the silence is not proof of absence. It is simply the place where the universe has not yet spoken to us, and may never need to. Why the light from some stars is older than Earth itself. Some of the light touching your eyes tonight began its journey before Earth had oceans, mountains, or even a surface to stand on. That thought feels almost impossible at first, because light seems instant in daily life. You flip a switch, and the room appears. The sun rises and morning arrives. But across the universe, light becomes a traveler, and distance turns into time. Earth is about 4.5 billion years old, yet telescopes can collect light from distant galaxies that has been traveling for longer than that, meaning those photons left their stars before our planet existed. They crossed expanding space while Earth was still only a future possibility inside a cloud of gas and dust around the young sun. This does not mean the same star is still exactly as it was when the light began. Many stars change, burn out, explode, or fade across cosmic time. What reaches us is not the current state of a distant object, but a preserved message from its past. In that sense, Astronomy is not only looking across space, it is reading delayed history. A galaxy billions of light years away is not shown to us as it is now, but as it was when its light escaped. You are not seeing a live broadcast of the universe. You are seeing old news delivered by the fastest messenger nature allows. And the farther away the source, the older the message becomes. This is why deep space images can feel so strange. They are not merely photographs of remote places, but layers of time stacked into one view. Nearby stars show us a more recent cosmic neighborhood, while distant galaxies reveal epochs older than Earth itself. The sky becomes a memory archive, written in starlight, where every faint glow carries the age of its journey. And this teaches something quietly profound. The present is not the same everywhere you look. Your eyes collect many different pasts at once. One point of light may be from years ago, another from millions of years ago, another from before the planet beneath you had formed. So when you look upward, you are standing in the present while being surrounded by ancient arrivals. The universe does not hand you one single now. It gives you a mosaic of vanished moments, each still moving, still arriving, still able to touch a human mind long after its source may have changed forever. And perhaps that is the softest wonder of all. Earth is young compared with some of the light we receive. Yet here you are, made of matter from earlier stars, awake beneath a sky filled with messages older than your world, learning that even darkness can carry memory across time. How we can see the past by looking into space. Every telescope is a time machine, but it does not carry you backward. It lets the past arrive quietly at your eyes. The reason is simple and strange at the same time. Light takes time to travel. In daily life, that delay is so tiny that the world feels instant, but space is so vast that even light, the fastest messenger in nature, needs time to cross it. When you see the moon, you see it as it was a little more than a second ago. When sunlight warms your face, you are feeling energy that left the sun about 8 minutes earlier. If the sun suddenly vanished, Earth would not know immediately. The last light and gravitational influence would continue reaching us for those same minutes. This is not because space is magical, but because information cannot arrive instantly. The farther you look, the older the view becomes. A nearby star may show you light from a few years ago. A distant nebula may show you a scene from thousands of years ago. A far galaxy may show you an era from millions or billions of years in the past. So astronomy is not only the study of places, it is the study of delayed moments. Telescopes do not show the universe in one shared present. They collect different ages of reality and place them side by side. This is why deep space images are so powerful. They are not just beautiful pictures. They are layered records. The faintest galaxies in a deep field are not merely far away in distance, but far back in cosmic history. Their light began its journey when the universe was younger, when galaxies were still growing, colliding, and building the structures we see around us today. Scientists use this delay as a gift. By looking farther away, they can study earlier stages of cosmic development, almost like reading older chapters of a book whose later pages surround us. They can compare young galaxies with mature ones, trace how stars formed over time, and understand how the universe changed from a simpler, hotter past into the vast, structured cosmos we live inside now. But this also means the universe is never shown to us live. The sky is a collection of memories, some recent, some ancient, all arriving together in the quiet theatre of night. And that should make you pause. You spend your life believing the present is a single moment shared by everything, but space teaches otherwise. The farther your vision reaches, the more the present dissolves into history. Looking outward becomes a way of looking backward, not through fantasy, but through physics. And perhaps that is why the stars feel so gentle and so haunting at once. They remind you that the past is not always gone. Sometimes it is still traveling. Sometimes it crosses the dark for years beyond counting, until one night it reaches a small planet, enters a human eye, and becomes understanding. Why the universe has no center. There is no throne in the universe, no sacred middle point from which everything is measured. And that may be one of the hardest truths for the human mind to accept. You are used to places having centers: the center of a room, the center of a city, the center of a storm, the center of a galaxy. So when you hear that the universe is expanding, it feels natural to ask where the expansion began and which place sits at the middle of it all. But the universe does not seem to work like an explosion from one central point into surrounding space. Instead, every distant region sees other distant regions moving away in a broadly similar way. Not because each place is secretly the center, but because there is no special center at all. The expansion is not arranged around Earth, the Milky Way, or any chosen galaxy. From a faraway galaxy, the view would also make it seem as though other galaxies are receding from there. This is not a trick of ego. It is a clue about the structure of space on the largest scales. A helpful comparison is the surface of Earth. You can walk on it without ever finding an edge or a single central point on the surface itself. The true center of Earth lies inside the planet, not on the surface where you live. In a deeper and more difficult way, the universe may have no center within the space we can access, because center is not always a meaningful idea for the whole cosmos. There are local centers, of course. The sun is near the center of the solar system's motions. A black hole may sit near the center of a galaxy. A cluster of galaxies may have a central region. But the universe as a whole does not appear to give one location cosmic importance over all others. On very large scales, galaxies are spread in a way that looks broadly similar in every direction, as if the cosmos refuses to point toward a privileged address. And this carries a quiet emotional weight. For centuries, humans slowly learned that Earth was not the center of the solar system, the sun was not the center of the galaxy, and the Milky Way was not the center of everything. Each discovery moved us farther from the comforting idea of being physically central. But maybe losing the center does not make you meaningless. Maybe it frees the universe from needing a throne at all. You do not have to stand at the middle of reality to matter inside it. A note in a song is not meaningless because it is not the first note. A candle is not less real because it does not sit at the center of the room. The universe having no center means existence is not built like a kingdom with one chosen seat. It is more spacious, more democratic, more mysterious than that. Wherever you stand, the cosmos opens around you. Wherever another mind may stand, it would open around them too. And perhaps that is the soft lesson hidden in this enormous fact. The universe does not revolve around us, yet it still allows us to understand it, to question it, and to feel wonder inside a place that has no center but somehow still makes room for awareness, the mystery of what came before the Big Bang. The most dangerous word in cosmology may be before, because it sounds simple until you place it at the beginning of everything. You can ask what happened before a storm, before a birth, before a star formed, because those events happen inside time, with earlier moments waiting behind them. But when you ask what came before the Big Bang, you are asking whether time itself had a past. And that is where the mind begins to lose its familiar ground. The Big Bang, in modern science, is not a filmed moment of creation that we can rewind to a perfect first frame. It is the name we give to the early hot, dense state from which the observable universe evolved. We can trace the universe backward with strong evidence. Galaxies were closer together, the cosmos was hotter, matter was more compressed, and the oldest light still carries a faint record of that early condition. But as we push closer and closer to the beginning, our current theories stop being fully reliable. Gravity, matter, space, and quantum behavior all crowd into one extreme situation, and we do not yet have a complete theory that can describe it with confidence. That means the honest answer is not a dramatic certainty. It is a carefully guarded mystery. Some ideas suggest that there may have been a phase before the hot Big Bang, such as cosmic inflation, when space expanded incredibly rapidly for a tiny fraction of time. Other models imagine a universe that bounced from a previous contracting phase, as if collapse turned into expansion. Some proposals suggest that asking before may be meaningless, Because time may have emerged with the universe itself, the way direction on Earth changes meaning at the pole. None of these possibilities should be sold as proven truth. They are attempts to approach a locked door using mathematics, observation, and imagination restrained by evidence. And that restraint matters. Real science does not make the mystery smaller by pretending to solve it too soon. It lets the unknown remain unknown until nature gives a reason to move further. Still, the question changes you, because if time had a beginning, then before may be a word your brain borrowed from everyday life and carried too far. If there was something before, then the Big Bang may not be the absolute origin, but a transition from a deeper state we have not yet learned to see. Either way, the mystery is not empty. It teaches humility. You live in a universe whose early chapters are partly readable, partly burned, and partly written in a language we have not finished learning. The beginning is not just a point in the past. It is a boundary around human understanding. And as you sit inside this vast unfolding, made of atoms that arrived long after that first fire, the question remains softly alive. Did time awaken once? Or has reality been breathing in forms we cannot yet imagine? Why space itself can stretch. Space is not an empty stage where the universe performs. In modern physics, space is part of the performance itself. For a long time, it was easy to imagine space as a fixed background, a silent container where planets moved, stars burned, and galaxies drifted. But Einstein's picture changed that deeply. Space is not perfectly rigid. It can be curved by mass, shaped by energy, and on the largest scales, its distances can change over time. This does not mean space is a rubber sheet in a literal sense, or that you would feel your room slowly stretching apart. Small systems like atoms, people, planets, solar systems, and galaxies are held together by forces strong enough to resist cosmic expansion. The stretching matters most across enormous distances, between galaxy clusters that are not tightly bound to each other. What stretches is not the objects themselves, but the separation between faraway regions. One of the clearest clues comes from light. When light travels across expanding space for billions of years, its wavelength is stretched too, shifting it toward redder colors. This redshift is not just a color change, it is a message from the journey itself, telling us that the space the light crossed was not static. It grew while the light was moving through it. In this way, the universe becomes less like a warehouse filled with objects and more like a living geometry, where distance is not always permanent. That idea is difficult because your senses were trained on solid things: floors, walls, roads, bodies. You expect distance to be something measured, fixed, and finished. But the cosmos asks you to think more softly. Distance can have history. The space between two galaxies can be different tomorrow than it is today. Not because the galaxies are pushing through space like ships through water, but because the scale of the universe itself is changing. This is why stretching space is not just a poetic phrase. It is a way of describing a real feature of the universe. The fabric of distance can evolve. And once you understand that, the cosmos feels less like a frozen diagram and more like a quiet unfolding. Even the gaps between things are not passive. Even emptiness has behavior. Even the invisible room in which everything happens can change with time. So, when you hear that space itself can stretch, do not picture ordinary matter being pulled thin or stars torn away from their own gravity. Picture the deeper rules of measurement slowly changing across the largest scales, making the universe more spread out, cooling its light, widening its history, and reminding you that reality is not only made of things, it is also made of the distances between them. How? The universe may be much bigger than we can ever know. The universe may be so large that the word large begins to lose its meaning before the universe itself runs out. What we call the observable universe is only the region from which light has had enough time to reach us. But that does not mean reality stops there. It only means our information stops there. Beyond the farthest things we can detect, space may continue with more galaxies, more dark regions, more structures, and perhaps more patterns than any telescope can ever confirm. Scientists do not currently know whether the whole universe is infinite or simply so enormous that our visible region is like one small window in a wall that goes on beyond sight. One reason this idea is taken seriously is that the early universe may have gone through an extremely rapid expansion called inflation, stretching space so dramatically that the part we can observe today might be only a tiny local patch of something far greater. Another clue comes from the shape of space. Measurements suggest that, on the largest scales we can study, space appears very close to flat, meaning it does not show an obvious strong curve back on itself within our observable range. That does not prove the universe is infinite, but it does allow the possibility that if it is finite, it may still be vastly larger than the portion we can ever see. And this is where the mystery becomes more than size. There may be parts of the cosmos that are real, physical, and full of history, yet permanently beyond evidence because no signal from them can ever reach us. They are not hidden behind a curtain we might one day pull back. They may be outside the boundary of possible contact. This teaches a quiet but powerful lesson about knowledge. Science can reach astonishingly far, but it is still limited by what the universe allows to arrive. We can build better telescopes, sharper detectors, and deeper theories, but we cannot demand information from regions forever disconnected from us. So the universe may not only be bigger than we know, it may be bigger than knowing itself. And perhaps that is the most humbling thought. You live inside a cosmic neighborhood vast enough to contain hundreds of billions of galaxies, yet that entire grandeur may be only the near shore of something immeasurably greater. The unseen beyond is not a fantasy we can claim as fact, but a possibility forced open by the limits of observation. When you look into deep space, you are not looking at the whole ocean. You are looking at the water that could send waves to you. Beyond that, the sea may continue in silence, not because it is empty, but because it is forever too far to speak. Why darkness is the most common thing in the cosmos? Darkness is not the universe's decoration. It is its default condition. The bright things you see in space are rare exceptions. Small furnaces scattered across distances so enormous that even the nearest stars feel like isolated sparks in a cold and spacious hall. This is why darkness is the most common thing in the cosmos. Not because the universe has nothing in it, but because most places are not close enough to a star for light to feel strong, warm, or visible the way it does on Earth. A star may be unimaginably powerful, but its light spreads outward in every direction, becoming weaker as it travels, thinning into a faint whisper across the vastness. By the time starlight crosses interstellar or intergalactic distances, much of it is too dim for human eyes, too stretched into invisible forms, or simply too far away to fill the sky with brightness. This also helps answer an old and beautiful puzzle. If there are so many stars, why is the night sky dark? If the universe were endless, unchanging, and filled with stars forever in every direction, the sky might glow much more brightly. But the universe has a history. Stars have not existed forever. Light has had only a limited time to travel. Many stars are too far, too faint, or too young in cosmic terms for their light to reach us as a bright wall. And between the glowing islands of galaxies, there are immense regions where no nearby sun dominates the view, only thin traces of radiation and the long silence of distance. Darkness, then, is not a failure of light. It is what remains when light has not arrived strongly enough to matter to your senses. On Earth, you are surrounded by reflected sunlight, glowing screens, lamps, fire, and atmospheres scattering blue across the day. You are trained to think brightness is normal. But step away from a planet, away from an atmosphere, away from a nearby star, and the universe reveals its quieter truth. Light is precious because it is local. Warmth is rare because it needs a source. Visibility is not guaranteed. It is a gift created by the right distance, the right matter, the right observer. This should not make the cosmos feel empty or hopeless. It makes every bright thing more meaningful. Every star is a temporary resistance against darkness, a burning island that turns hidden matter into visible story. Every sunrise is not ordinary at all, but a nearby star lending its power to a small turning world. And when you look into the night, you are not seeing darkness as an enemy of the universe. You are seeing the vast background against which every light becomes noticeable. The cosmos is mostly dark because space is vast. Stars are finite. Light needs time, and your eyes are fragile instruments tuned to only a narrow kind of glow. Yet inside that darkness, a few photons still cross impossible distances and arrive here, gently proving that even in a universe ruled by shadow, light does not need to be everywhere to matter. The strange silence between the stars. A star can die in an explosion powerful enough to outshine an entire galaxy. And still, if you were floating nearby in the vacuum of space, you would hear nothing. That is the strange silence between the stars. It is not silence in the ordinary sense, like a quiet room after midnight, because a room still has air to carry vibrations into your ears. Space has no thick blanket of air, no ocean of molecules pressed close together, no easy path for sound to travel the way it does on Earth. Sound is not a thing that flies by itself. It is a pattern of pressure moving through matter. It needs something to shake. On Earth, a clap becomes sound because air molecules bump into one another, passing the disturbance forward until it reaches your ear. Between the stars, matter exists, but it is spread so thinly that a human ear would have almost nothing to receive. This means the most violent events in the universe are not accompanied by the kind of roar your instincts expect. A supernova does not boom through space like thunder. Two stars tearing material from each other do not scream. A comet drifting between worlds does not whistle in the dark. The universe can be physically active and acoustically silent at the same time. Yet this does not mean space has no vibrations at all. In clouds of gas, inside stars, around planets with atmospheres, and within magnetic fields filled with charged particles, waves can move. Scientists can even translate certain space signals into audio, turning data into sounds humans can hear. But those are interpretations, not literal noises traveling through empty space into an unprotected ear. This distinction matters because it teaches you how much of reality depends on the kind of body you have. Your ears evolved for air, footsteps, voices, danger, rain, and breath. They were never designed to listen to the deep spaces between suns. So when the cosmos appears silent, it is partly because the universe is mute there, and partly because you are made for a different environment. The silence between the stars is not peaceful because nothing happens. It is peaceful because events do not always need sound to be real. Radiation can flash, matter can collapse, gravity can pull, magnetic storms can twist, stars can be born and destroyed, and still, across the vacuum, no thunder follows. There is something humbling in that. Human life is full of noise, as if importance must announce itself loudly. But the universe performs its greatest changes in a quiet that no ear can enter. The silence between the stars is not emptiness. It is the absence of a messenger your senses understand. It reminds you that reality does not become less powerful when it stops being audible. Sometimes the deepest forces move without a voice, and the cosmos, vast and awake, continues its work in silence. Why some stars, you see, may already be dead. Some lights in the sky may be beautiful ghosts, still arriving long after the star that released them has changed forever. When you look upward, it feels as if every star is present right now, burning in the same moment you are breathing beneath it. But the sky is not a live window. It is a delayed message system, and every point of light carries the age of its journey. For many nearby stars, this delay is short on cosmic scales, years, decades, centuries. And because most stars live for millions or billions of years, they are probably still there in some form when you see them. That part matters, because it would be misleading to say that most stars in your night sky are already dead. They are not. Many are long-lived stable suns, quietly burning through their fuel far more slowly than a human lifetime can notice. But some stars, especially very massive ones, live much shorter and more violent lives. They burn through their fuel quickly, swell, collapse, or explode as supernovae, leaving behind neutron stars, black holes, or fading remnants. If such a star is far enough away, its light can continue crossing space even after the star itself has already died. What reaches you is not the star's current condition, but the last report that had enough time to arrive. A red supergiant like Betelgeuse, for example, is often discussed because it is near the end of its life in astronomical terms. But even if it exploded, we would only know after its light crossed the distance between us and it. The universe does not update instantly. It lets history travel at the speed of light, and until that history arrives, the past remains visible. Through telescopes, this becomes even more dramatic. We can observe stars in distant galaxies whose light began traveling before human beings existed, before mammals rose, sometimes before Earth's surface looked anything like the world you know. Some of those stars may no longer exist, yet their light is still real, still measurable, still carrying information about their temperature, elements, and motion. This makes the night sky feel less like a collection of objects and more like a field of delayed memories. You are not simply seeing stars, you are receiving moments. Some moments are young, some are ancient, some may belong to things that have already transformed into something else. And this should change the way you think about presence. A thing can be gone and still touch you. A star can die and still keep teaching. Light does not ask whether its source survived. It keeps moving, crossing the dark with patient loyalty. So when you see a faint point overhead, do not imagine only a distant fire. Imagine a message released from a place you cannot reach, traveling through years of silence, arriving just in time to enter your eye. Maybe the star is still burning. Maybe it has already become a remnant. Either way, what you receive is true. Not the truth of now, but the truth of then. And in that quiet delay, the sky becomes a lesson about time itself. Nothing we see is purely present, and even what has ended may continue shining for someone far away. How tiny quantum fluctuations became galaxies. The first galaxies began as almost nothing at all. Tiny trembles in the early universe, so small they were not stars, not dust, not even clouds, but slight unevenness in the fabric of reality itself. In the earliest moments after the Big Bang, the universe was extremely hot, dense, and almost smooth. But almost is the key word. Quantum physics says that even in the calmest looking state, nature is never perfectly still. At incredibly small scales, there are tiny fluctuations, little variations in energy that appear not as dramatic explosions, but as soft uncertainties built into the foundation of the universe. Normally, such microscopic changes would remain microscopic, but the early universe appears to have gone through a brief period of extremely rapid expansion, and during that expansion, these tiny fluctuations were stretched across enormous distances. What began as a small quantum wrinkle became a large-scale difference in density. One region had slightly more matter, another slightly less. At first, the difference was almost unimaginably subtle, but gravity is patient. Given enough time, the slightly denser regions pulled in more matter. More matter meant stronger gravity, and stronger gravity pulled in even more. Slowly, the early smoothness began to break into structure. Gas gathered. Dark matter helped shape invisible gravitational wells. The first stars formed inside these growing regions, and later, groups of stars collected into young galaxies. This is one of the most astonishing ideas in modern cosmology. The grand architecture of the universe may have grown from tiny quantum irregularities, amplified by expansion and sculpted by gravity over billions of years. A galaxy with hundreds of billions of stars, spiral arms, glowing gas, dust lanes, and possible worlds may trace its deepest origin back to a fluctuation far smaller than anything your senses could ever touch. This does not mean galaxies appeared by magic. It means small differences, under the right conditions, can become enormous consequences. The universe did not need to be perfectly designed in every detail. It needed slight imbalance, time, gravity, and enough patience for structure to emerge. And perhaps that is what makes this story so quietly powerful. The cosmos did not begin as a finished painting. It began with nearly uniform light and matter, with tiny seeds hidden inside what looked almost smooth. Those seeds became clusters, galaxies, stars, planets, and eventually minds capable of asking where it all came from. So when you look at a galaxy, you are not just seeing a city of stars. You are seeing the long memory of a small beginning. You are seeing how a whisper in the early universe became a luminous island in space. And in that, there is a lesson that reaches beyond astronomy. Not every beginning needs to be loud to matter. Some of the greatest structures in existence began as something almost invisible, waiting for time to reveal what it could become. Why reality was once smaller than an atom. There was a time when everything you can now see across the sky may have belonged to a region smaller than a single atom. Not because stars and galaxies were crushed like objects in a box, but because the universe itself was once in an unimaginably hot, dense, and compressed state. This idea sounds unreal because your mind wants size to behave normally. A planet is large, an atom is small, a galaxy is vast, an empty space lies between things. But in the earliest universe, the familiar separation between things had not yet developed into the cosmic landscape we recognize. Matter was not arranged into stars. Atoms had not formed. Light could not travel freely the way it does now. The part of the universe that would eventually become everything observable to us today was packed into a state so extreme that ordinary comparisons almost fail. And there is an important truth here. Scientists are careful not to claim that the entire universe, especially if it is infinite, was literally a tiny ball sitting in some outside darkness. What we can say is that the region that became our observable universe was once compressed to a scale far smaller than anything in everyday experience, perhaps smaller than an atom during the earliest moments we try to describe. Then space expanded, cooled, and allowed structure to unfold step by step. Energy became particles. Particles later formed simple atomic nuclei. Much later, atoms formed. After that, gravity slowly gathered matter into the first stars and galaxies. So when you look at the vast sky, you are not looking at something that was always spread out like this. You are looking at a reality that unfolded from a state where distance itself was radically different. The size of things did not simply increase like a photograph being enlarged. The relationships between places changed. Space grew, and as it grew, the universe became less dense, less hot, and more capable of complexity. This is one of the deepest lessons of cosmology. Vastness may have begun as compression, and complexity may have begun as simplicity under pressure. The quiet galaxy above you, the iron in your blood, the oxygen in your lungs, the photons entering your eyes. All of it traces back to an era when the ingredients of everything were not yet separated into the world you know. And perhaps that is why this fact feels so strange. It tells you that the universe was not born looking cosmic. It did not begin with stars scattered beautifully in darkness. It began in a condition so extreme that space, matter, and time were woven together in ways our current theories can only partly explain. The calm night sky is therefore not the opposite of the early universe. It is what the early universe became after billions of years of expansion, cooling, and patient transformation. So when you hear that reality was once smaller than an atom, do not picture a tiny marble floating in emptiness. Picture the observable cosmos folded into a beginning where scale had not yet opened, where all future distance waited in silence, and where the immense universe you know was still only a possibility, held inside a beginning too small for the human mind and too powerful to ever fully leave behind. The cosmic horizon we can never cross. There are places in the universe that are not blocked by walls, guarded by black holes, or hidden behind darkness, and yet they are already beyond every journey you could ever take. This is the cosmic horizon we can never cross, not a solid edge in space, but a limit created by the future itself. It is different from simply saying something is far away. Distance alone can be crossed in principle if you have enough time, enough energy, and a path that remains reachable. But the universe is not only large, its expansion is changing what reachable means. Because the expansion of space appears to be accelerating, there are galaxies so distant that even if you sent a signal toward them today at the speed of light, that signal would never arrive. It would move forward locally as fast as nature allows, yet the space between here and there would keep growing in such a way that the destination slips farther out of possible contact. This horizon is not something you would crash into. A traveler would not see a glowing barrier or a warning line across the stars. The boundary is more subtle than that. It is written into the relationship between motion, distance, and cosmic expansion. Some galaxies we can still observe now are already unreachable in practice, because the light reaching us left long ago, when the universe was smaller and the path between us was less stretched. Their ancient image can enter our telescopes, but anything we send now could be forever too late. That makes the horizon strangely emotional. It means the universe contains places that are visible as memories but closed as destinations. You can study them, measure their light, learn from their past, and still never touch their future. It is like seeing a ship on the far ocean after the currents have already made return impossible, and this teaches a different kind of humility from ordinary distance. Human beings often imagine that better technology turns the impossible into the possible. But the cosmic horizon is not just an engineering problem. It is a limit set by the structure and history of the universe itself. No engine can simply overcome the way space expands on the largest scales. No ambition can demand that a future signal reach a region that has slipped outside causal contact. Yet this does not make the universe feel smaller. It makes every reachable moment more precious. The stars and galaxies whose light still arrives are not guaranteed companions forever. They are messages from a cosmos whose connections can fade with time. So when you think of the cosmic horizon, do not imagine the end of existence. Imagine the edge of possible exchange, the place beyond which events may happen. Stars may burn, and galaxies may change without ever being able to tell us directly. It is a quiet reminder that not everything real can be reached, not everything visible can be visited, and not every part of the universe belongs to our future. Why time may not flow the same everywhere. Time is not a single river flowing at the same speed through every corner of the universe. It is more like a rhythm that changes depending on where you are and how you move. This is one of the quiet revolutions of Einstein's relativity. Clocks do not all agree simply because they exist. On Earth, time feels steady because your body, your room, your city, and the people around you are all moving under similar conditions. Your watch, your heartbeat, and the sunlight crossing your window seem to belong to one shared present. But the universe is more subtle than that. A clock moving very fast ticks more slowly compared with a clock that is relatively still. A clock near a strong gravitational field also ticks more slowly compared with one farther away from that gravity. This is not philosophy or illusion. It has been measured with extremely precise atomic clocks. Even clocks placed at slightly different heights on Earth can tick at slightly different rates. Because gravity is a little stronger closer to the planet's surface, the effect is tiny in daily life, but it is real, and modern navigation systems like GPS must account for it. Satellites high above Earth experience time differently from clocks on the ground, and without correction, location calculations would slowly drift. So time is not just something that happens, it is something shaped by motion and gravity. Near a black hole, this becomes far more dramatic. To someone far away, a clock falling toward the edge of a black hole would appear to slow down more and more, as if time itself were struggling near the deep curve of gravity. But for the falling clock, its own seconds would still feel normal. That is the strange part. Time does not feel broken to the one living inside it. Your own moment always feels like the present. It is only when two paths are compared that the difference appears. This means the universe has no master clock hidden above everything. No perfect cosmic metronome forcing all events to unfold at one identical pace. Time is local. Time is relational. Time belongs to the path taken through space-time. And this changes the way you think about reality. You are used to believing that now is a universal thing, stretching everywhere at once. But relativity suggests that different observers can slice the universe's events in different ways, depending on how they move. The present is not as absolute as it feels from inside your skin. It is a human experience resting on deeper physical rules. And maybe that is why this idea feels so unsettling and beautiful at the same time. It tells you that time, the thing you trust most, the thing that carries every memory and every hope, is not rigid. It bends gently under gravity, stretches with motion, and refuses to be the same everywhere. So when you look at the sky, you are not only seeing places separated by distance, you are thinking about regions where clocks would disagree, where seconds could pass differently, where the universe keeps time in more than one tempo. And beneath that vast cosmic music, your own heartbeat is just one small rhythm, real and temporary, moving through a universe where even time has depth. How the universe remembers its own beginning. The universe has no brain, no memory, no hidden archive in the way a living mind does. And yet its beginning is still written into everything around us. This is what it means to say the universe remembers itself, not through thoughts, but through evidence. The early cosmos left traces behind, and those traces are still readable if you know where to look. One of the clearest is the faint afterglow spread across all directions of space, a leftover radiation from the time when the universe first became transparent enough for light to travel freely. It is not a picture of the absolute first instant, but it is a baby photograph of the cosmos, showing tiny differences in temperature that later helped matter gather into the structures we see today. There is also memory in the recipe of the universe itself. The amounts of hydrogen, helium, and a little lithium match what we would expect if the young universe was once hot and dense enough to forge simple elements before stars existed. Even the way galaxies are arranged in enormous patterns carries hints of early conditions, like ripples frozen into a pond long after the stone has disappeared beneath the surface. Scientists read these signs the way geologists read layers of rock, or biologists read DNA, not as guesses, but as records carried forward by physical processes. The universe does not remember by preserving a perfect movie of its birth. It remembers through scars, ratios, patterns, and echoes. Expansion tells us it was once more compressed. Ancient light tells us how smooth and uneven it was. Element abundances tell us what the first minutes allowed. The distribution of galaxies tells us how early seeds grew into cosmic architecture. And this is what makes the idea so quietly powerful. The past is not gone simply because it is unreachable. It has become structure. It has become temperature. It has become chemistry. It has become the background condition of every star, planet, and living body that came after. You are not separate from that memory. The atoms inside you exist because the universe followed a particular history, because its early heat cooled in a particular way, because matter survived, gathered, and changed. So when you look into space, you are not only looking outward, you are looking into a universe that has carried its beginning forward, not as a story told in words, but as a deep physical inheritance. The cosmos remembers by becoming what its beginning made possible, and you are one of the ways that memory has learned to wonder about itself. Why the far future of the universe looks so quiet? The far future of the universe does not look violent. It looks almost unbelievably calm, as if the cosmos slowly forgets how to make new fire. Today, the universe still feels alive with activity. Stars are forming in cold clouds, galaxies are merging, supernovae are scattering heavy elements, and black holes are feeding in bright, energetic regions. But this busy age cannot last forever. Stars need gas to form, and gas is not an endless resource inside galaxies. Over immense stretches of time, much of that gas becomes locked inside stars, stellar remnants, planets, or is heated and scattered so widely that it becomes harder to gather again. New star formation gradually slows, not all at once, but like a city whose lights go out district by district across an impossibly long night. The most massive stars disappear first because they burn their fuel quickly, while smaller stars can glow for far longer, quietly spending their energy with extreme patience. As the universe ages, the bright blue light of young stars becomes rarer, and many galaxies may grow redder, dimmer, and quieter, filled more with old stars and remnants than with fresh stellar birth. At the same time, cosmic expansion continues to stretch the distances between large groups of galaxies, making the wider universe look more isolated from any one region. A civilization in the very far future might look up and see a sky with fewer visible signs of the grand cosmic web, not because the universe has vanished, but because light from distant structures has become harder or impossible to receive. The future is quiet then, not because nothing exists, but because the universe becomes less efficient at creating dramatic change. Its fires burn lower. Its collisions become rarer in reachable space. Its bright signals fade into colder, longer wavelengths. The cosmos shifts from an age of construction to an age of endurance. And there is something deeply humbling in that. We live during a relatively luminous chapter, when stars still form, galaxies still reveal their shapes, and the night sky still carries enough light to tell a rich story. The far future reminds you that brightness is not the universe's permanent mood. Activity is a phase, fire is a season. Even the largest structures are temporary arrangements inside time. So when you imagine the distant fate of everything, do not picture a sudden ending, like a curtain falling. Picture a long, soft dimming, a gradual settling, a universe growing quieter not in defeat, but in exhaustion, after spending its ancient energy across stars, galaxies, and the fragile minds that once looked up and asked where all the light was going. The Big Bang was not an explosion into space. The name Big Bang makes your mind hear an explosion, but the universe did not begin like a bomb going off in a dark room. There was no empty space waiting outside, no central spark throwing galaxies into a surrounding void, no shockwave racing through a cosmic atmosphere. The phrase is misleading if you take it too literally. What modern cosmology describes is not matter exploding into space, but space itself beginning in a much hotter, denser state, and then expanding everywhere at once. Every region of the observable universe was once much closer together, not because all galaxies were piled into one place inside a larger container, but because the distances between all places were dramatically smaller. This is difficult because your everyday mind understands explosions very well. A firework bursts from a point, smoke spreads into air, stones scatter from an impact. But the early universe was not an object inside a background. The background was part of the event. Space was not the empty theatre waiting for matter to enter. Space was woven into the unfolding itself. This is why there is no single location in the sky where the Big Bang happened. It happened everywhere, because everywhere we can observe today was once part of that early hot, dense condition. If you could rewind cosmic history, galaxies would not fly back toward one special center. The distances between all unbound regions would shrink. The whole observable cosmos would become hotter, denser, and simpler. At first, there were no stars, no planets, no atoms as you know them, no quiet night sky. There was a young universe filled with intense energy, changing rapidly, cooling as it expanded, slowly becoming able to form particles, then simple nuclei, then atoms, then much later, the first stars. The Big Bang Theory does not claim to explain the absolute first cause with perfect certainty. It describes how the universe evolved from an early hot, dense state using evidence we can still measure today. That honesty matters. Science is not saying we know every mystery of the beginning. It is saying the universe carries signs that it was once very different from what it is now. And maybe this is the deeper lesson hidden inside the correction. The beginning of the universe was not a loud blast in space, but a transformation of space, time, matter, and energy together. It was not chaos thrown outward from a point, but the opening of the stage on which distance, structure, and history would later appear. So when you hear Big Bang, do not picture an explosion lighting up emptiness. Picture the earliest chapter of expansion, a universe too hot for stars and too dense for familiar form, slowly cooling into the possibility of galaxies, worlds, and eventually a mind like yours. looking back and trying to understand the beginning without turning it into something too small. The early universe was hotter than any star. Before the first star ever burned, the universe had already been hotter than any star could ever hope to be. That sounds strange because stars feel like the natural symbol of heat. Their cores fuse atoms, their surfaces blaze, and their light can warm planets across millions of kilometers. But stars are latecomers. They formed only after the universe had expanded, cooled, and become calm enough for matter to gather. In the earlier stages we can meaningfully describe, the cosmos was not a dark place waiting for stars to appear. It was a dense, blazing state of energy and particles, so hot that atoms could not exist. And even the building blocks of atoms were moving in a violent sea of interactions. Heat, in physics, is not just fire or flame. It is the restless motion and energy of particles. And in the young universe, everything was packed so closely and energized so intensely that ordinary matter had not yet settled into the familiar forms you know. There were no solid worlds, no glowing stellar surfaces, no empty spaces between suns. There was only an early cosmic furnace, everywhere at once, where the conditions were far beyond the inside of any modern star. As the universe expanded, it cooled. That cooling was not weakness. It was the beginning of possibility. When things were too hot, complexity could not survive. Particles collided too fiercely. Light could not travel freely. Matter could not assemble into stable atoms. But as the temperature dropped, the universe began to change its language. Simple particles could combine. Later, atomic nuclei could form. Much later still, electrons could settle around nuclei and create atoms, allowing light to move through space more freely. Only after long ages of further cooling and gravitational gathering could stars ignite. So stars, bright as they are not the universe at its hottest. They are children of a universe that had already cooled enough to become structured. This reverses the way your intuition wants the story to go. You might imagine the cosmos beginning in darkness and slowly warming as stars appeared, but the truth is closer to the opposite. It began in overwhelming heat and slowly cooled into darkness, stars, galaxies, and eventually life. The fire came first, but it was not a fire with flames. It was heat as a condition of reality itself. And maybe that is the deeper lesson. Sometimes creation does not begin with gentle order. Sometimes it begins with conditions too extreme for anything familiar to exist. And only through cooling, spacing, and waiting can beauty appear. Every calm star in the sky is evidence that the universe survived its own intensity. Every atom in your body exists because the cosmos became cooler than it once was. You are not living after the fire went out. You are living in the quiet world the first heat made possible. How the first atoms formed in darkness. The first atoms were born when the universe became calm enough for matter to finally hold itself together. Before that moment, the cosmos was not empty, but it was not yet transparent, not yet filled with stars, and not yet shaped into the familiar world of chemistry. It was a hot, glowing fog of particles and light, where electrons moved too freely and too violently to settle around atomic nuclei. Every time an electron tried to join with a nucleus, energetic light would knock it loose again, as if the young universe was too restless to allow even the simplest form of stillness. But expansion slowly changed everything. As space grew, the universe cooled. And after hundreds of thousands of years, the energy of light dropped low enough that electrons could finally remain attached to nuclei. This was when the first true atoms formed, mostly hydrogen, with some helium and tiny traces of other simple elements. It sounds like a small step, but it transformed the universe. Before atoms formed, light was trapped in a thick cosmic mist, constantly scattering off free electrons. After atoms formed, light could travel freely through space for the first time. The universe cleared, but strangely, this new transparency did not immediately create a sky full of stars. There were no suns yet, no galaxies shining, no planets reflecting light. Once the early glow faded and stretched into wavelengths invisible to human eyes, the cosmos entered a long period often called the Dark Ages. It was dark, not because nothing existed, but because the first stars had not yet ignited. The ingredients were there: hydrogen gas, helium gas, gravity, and tiny uneven regions where matter could begin to gather. But the universe had to wait. Gravity needed time to pull gas into denser pockets, to compress it, to warm it, and eventually to create the first stellar fires. This means the first atoms formed in a universe that had become clear but not yet luminous. A universe with matter but no starlight, with structure beginning silently before beauty became visible. And this is the quiet lesson hidden inside that early darkness. Creation does not always look bright at first. Sometimes the most important change is not the moment something shines, but the moment it becomes possible for shining to happen later. The first atoms were simple, almost humble, but without them there would be no stars, no galaxies, no water, no planets, no bodies, no breath, no eyes to look back into the past. In the darkness before the first stars, the universe was not dead. It was preparing. It was holding the first letters of a language that would one day spell out worlds, life, memory, and wonder. The cosmic microwave background, the oldest light we can see. The oldest light we can still detect is not starlight at all, but a faint cooled whisper from a time before the universe had stars to shine. This ancient signal is called the cosmic microwave background, and it is one of the most important pieces of evidence we have for the early universe. It does not come from a single star, galaxy, or explosion in one direction. It comes from every direction at once, surrounding us like a dim afterimage of the young cosmos. To understand it, you have to go back to a time when the universe was filled with a hot, dense fog of particles and light. Light existed, but it could not travel freely, because free electrons kept scattering it again and again, trapping it inside a glowing mist. Then, as the universe expanded and cooled, electrons joined with nuclei to form atoms, and suddenly light had space to move. That released light has been traveling ever since. But during its long journey, the expansion of the universe stretched it from visible and infrared light into microwaves, far too cold and faint for human eyes. Today, it appears as a nearly uniform background glow, only a few degrees above absolute zero, spread across the entire sky. What makes it extraordinary is not only its age, but its detail. It is almost perfectly even, yet not completely. It contains tiny temperature differences, little variations that reveal where matter was slightly denser or thinner in the early universe. Those tiny differences became the starting map for future structure, guiding where galaxies and clusters would eventually grow. So the cosmic microwave background is not just old light. It is a fossil of the universe before stars, before planets, before life, before anything familiar had formed. It is the closest thing we have to a baby picture of the cosmos, not showing the absolute first instant, but showing the universe when it first became transparent enough to let light travel freely. And this should make you feel the sky differently. Beyond the bright stars and dark spaces, there is an ancient glow everywhere, too faint for your eyes, but real enough for instruments to measure. The universe has carried this signal for billions of years, stretched it, cooled it, softened it, but never erased it. In that faint microwave light, the beginning did not vanish. It became background. It became evidence. It became a quiet message still arriving from every direction, reminding you that the universe is not silent about where it came from. It is speaking softly in the oldest light we can see. Why the first stars changed everything. The first stars did not simply light up the universe. They changed what the universe was able to become. Before them, the cosmos had matter, gravity, and darkness, but it did not yet have the rich chemistry needed for planets, oceans, rocks, or bodies like yours. The earliest stars were probably very different from most stars we see today. They formed from almost pure hydrogen and helium because heavier elements had not yet been made in large amounts. Without those heavier elements to help gas cool and fragment easily, many of the first stars may have grown enormous, far more massive than the Sun, burning with fierce intensity and living short, dramatic lives. Their light was not just decorative, it began to transform the space around them. Powerful ultraviolet radiation tore electrons away from hydrogen atoms in surrounding gas, helping to end the long cosmic dark ages and begin an era when the universe became more transparent to certain kinds of light. This process, called rayonization, was one of the great turning points in cosmic history. The universe was no longer merely waiting in darkness, it was being reshaped by its first sources of radiation. But the first stars changed everything in an even deeper way when they died. Inside their cores, and especially in their explosive deaths, they created and scattered heavier elements such as carbon, oxygen, silicon, and iron. These elements did not exist in the early universe in the form needed to build complex worlds. They had to be forged. They had to be released. A star had to live, burn, collapse, and break open so that future generations of stars could be born from richer material. That means the first stars were not only lights, they were cosmic ancestors. They turned a simple universe into a chemically creative one. After them, gas clouds could contain new ingredients. Later stars could form with planets around them. Rocky worlds could appear. Chemistry could grow more complex. Eventually, under the right conditions, life could become possible. This is why those first stars matter so much. They were the bridge between a universe made mostly of simple gases and a universe capable of forests, oceans, bones, and memory. And there is something quietly moving about that. The first stars may be gone now, too distant and ancient for us to see directly as individual objects. But their influence remains everywhere. Every breath you take depends on a universe that learned how to make oxygen. Every drop of blood carries elements that had to be cooked inside stars. Every stone beneath your feet belongs to a cosmic story that began when the first stellar fires changed the darkness into possibility. So when you think of the first stars, do not imagine only beautiful lights appearing in an empty sky. Imagine the moment the universe began preparing itself for complexity, the moment darkness became fertile, the moment the cosmos learned how to make more than light. How gravity turned tiny clumps into galaxies. Gravity is the universe's slowest sculptor, and given enough time, even the faintest clump of matter can become a city of stars. In the young universe, matter was not arranged neatly into galaxies. It was spread out unevenly, with some regions just slightly denser than others. Those small, crowded regions mattered because gravity is sensitive to difference. A place with a little more matter pulls a little more strongly, and over time, that stronger pull draws in even more material. This creates a quiet feedback. More matter makes more gravity, and more gravity gathers more matter. But galaxy formation was not instant, and it was not simple. Ordinary gas alone would have struggled, because gas heats up when it collapses, and heat pushes outward, resisting further compression. For a clump to keep growing, it needed to lose some of that heat by radiating energy away. Cooling allowed gas to settle more deeply into gravitational wells, while invisible dark matter helped provide the larger framework. Dark matter did not shine or form stars, but because it responded to gravity and did not get pushed around by light in the same way ordinary gas did, it could begin gathering into large halos early on. These halos acted like hidden valleys, places where normal matter could fall inward, collect, spin, flatten, fragment, and eventually form stars. As more clumps merged together, small early structures became larger ones. Young galaxies grew not as perfect finished objects, but through a long process of attraction, collision, gas flow, star formation, and reshaping. Gravity did not build galaxies like a machine assembling parts. It grew them like weather grows storms, pulling, twisting, concentrating, and allowing patterns to emerge from imbalance. This is why galaxies are not random piles of stars. Their shapes carry the memory of motion. Disks from rotating gas, bulges from crowded centers, halos from ancient mergers, streams from smaller galaxies torn apart and absorbed. Every galaxy is a history of what gravity gathered and what time allowed. And this should make you see the universe differently. The great luminous structures in deep space did not appear because matter knew where to go. They appeared because tiny advantages became larger consequences. A slight crowding became a pull became a cloud became stars, stars became galaxies, and across billions of years, gravity turned small imperfections into the architecture of the cosmos. So when you look at a galaxy, you are seeing patience made visible, not a sudden creation, but the slow victory of attraction over emptiness. A reminder that even the largest forms in existence can begin as something barely stronger than the space around them. The cosmic web that connects galaxies. If you could step far enough back from the universe, galaxies would stop looking like scattered islands and begin to look like threads in a vast, dim web. This is the cosmic web, the largest known pattern in the universe. An enormous network of galaxy clusters, long filaments, thin sheets, and dark, open regions called voids. At human scale, space seems random because the distances are too large and the arrangement too difficult to feel. But when astronomers measure the positions of millions of galaxies, a hidden order appears. Galaxies are not spread evenly like dust in a room. They gather along long strands that can stretch for hundreds of millions of light years, meeting at dense knots where galaxy clusters form, while huge, empty-looking voids sit between them. This web is not made of solid strings. It is made of matter arranged by gravity across cosmic time, with galaxies lighting up the densest parts like lamps along invisible roads. Even gas between galaxies can follow these filaments, flowing slowly toward clusters and feeding the growth of galaxies over immense periods. The strange thing is that the biggest structure in the universe is not a single object you can point to, like a planet or a star. It is a pattern, a relationship between countless objects, a skeleton written across space itself. And this teaches something important. The universe is not only built from things, but from the way things are connected. A galaxy may look lonely in a telescope image, but on the largest scales, it belongs to a neighborhood, a strand, a crossing, a larger architecture. The cosmic web turns emptiness into geography. It shows that even the spaces between galaxies have shape, history, and direction. And perhaps that is why this idea feels so quietly powerful. You live inside a universe where connection is not just emotional or symbolic. It is physical, stretched across distances the mind can barely hold. The stars above you are not random sparks thrown into darkness. They are part of a vast structure, a delicate cosmic network where gravity has been slowly drawing matter into lines, knots, and open chambers for billions of years. So when you look into the night, do not think only of isolated lights. Think of a web too large to see from within, a silent architecture holding galaxies like dew on invisible threads, reminding you that even in the deepest space, nothing truly exists alone. Why galaxies form in long invisible threads? Galaxies are not sprinkled randomly through space. Many of them grow where the universe has already drawn invisible roads. These roads are not made of steel, dust, or shining gas, but of gravity's long memory, shaped mostly by dark matter and followed later by ordinary matter. In the young universe, matter did not collapse evenly in all directions. Some regions became slightly denser, and gravity pulled material inward. But the collapse happened unevenly, like a soft cloud being squeezed first into sheets, then into strands, and finally into crowded knots. Along those strands, gas could flow for millions and billions of years, slowly feeding the places where galaxies were forming. This is why galaxies often appear inside long filaments rather than isolated points in perfect emptiness. The filament is not a bright rope you can see with your eyes. Much of it is hidden. Dark matter creating the gravitational path, thin gas stretched between galaxies, and faint material too spread out to glow strongly. But its influence is real. Galaxies grow better where matter can keep arriving. A galaxy is not only born from a single cloud collapsing once. It can be nourished by streams of gas flowing along these cosmic filaments, like rainwater moving through river channels toward a valley. At the intersections of several filaments, matter gathers even more strongly, and those crowded crossing points can become galaxy groups or massive clusters. This means the shape of the universe affects the life of a galaxy before the galaxy even fully becomes itself. Its fuel, its growth, its mergers, even its future star formation, can depend on where it sits inside this invisible network. Scientists study these filaments through galaxy maps, gravitational effects, and the faint signatures of gas between galaxies, slowly revealing that the universe has a hidden architecture far larger than any single object. And this is the deeper lesson. Structure does not always announce itself with brightness. Sometimes the most important roads are unseen. A galaxy may look like a self-contained island of stars, but it is often connected to long supply lines of matter, shaped by forces that began working before the galaxy had a name, a shape, or a single star inside it. So when you think of galaxies forming in invisible threads, do not picture decoration in the sky. Picture the universe using gravity like a quiet hand, drawing matter into channels, guiding gas toward future suns, and turning faint lines of attraction into the places where light will eventually gather. The strange emptiness of cosmic voids. The emptiest places in the universe are not empty at all. They are vast cosmic deserts where matter exists so thinly that even galaxies become rare. These regions are called cosmic voids, and they are among the largest structures in the universe, not because they are filled with things, but because they are defined by an astonishing lack of them. A void can stretch across tens or even hundreds of millions of light years, containing far fewer galaxies than the dense regions around it. If you lived inside one, the night sky might look lonelier, with fewer bright galaxy neighbors beyond your own. But a void is not a perfect nothing. It can still contain dim galaxies, thin gas, dark matter, stray particles, and faint radiation. Its emptiness is relative, not absolute. The reason voids exist is tied to the same cosmic history that built crowded regions. Gravity slowly pulled matter away from less dense areas and toward denser ones. Over billions of years, the rich regions became richer, gathering galaxies into clusters and filaments, while the poor regions became poorer, expanding into enormous underfilled spaces. In that sense, voids are not failures of structure. They are part of the structure. They are the hollow spaces that help reveal the shape of the cosmic web around them. Scientists study them because they can teach us how gravity, expansion, and dark energy behave on the largest scales. A void is like a silence that helps you hear the music more clearly. Without the empty spaces, the pattern of the universe would be harder to understand, and this is what makes them so strange. The universe's architecture is not only written in stars and galaxies, but also in absence. The places where almost nothing gathers can be just as important as the places where everything crowds together. A cosmic void asks you to rethink emptiness. It is not meaningless. It has size, history, influence, and scientific value. It is a reminder that reality is shaped not only by what exists, but also by where existence becomes thin. So when you imagine the deepest voids, do not picture a blank mistake in space. Picture an immense quiet chamber, carved by billions of years of cosmic motion, where the universe reveals that even emptiness can have form. Why some parts of space are almost completely empty. Some regions of space are so empty that calling them empty almost feels too small, because their emptiness is not like an abandoned room. It is a thinning of reality across distances the human mind can barely hold. On Earth, even the cleanest room is crowded with air molecules, dust, warmth, moisture, and invisible motion. But in the deepest regions between galaxies, matter becomes spread so thinly that a volume larger than a house might contain only a few atoms. And in some cosmic voids, even less ordinary matter than the universe's already sparse average. This near emptiness happened because the universe did not keep matter evenly mixed. Over billions of years, gravity pulled gas, dark matter, and galaxies toward denser regions, leaving other regions increasingly drained. It is not that something swept those places clean like a broom. It is that matter followed attraction elsewhere. The crowded areas became galaxy clusters and filaments, while the neglected regions became vast, low-density zones, like valleys of absence between mountains of structure. Expansion also played its part, stretching space and diluting whatever remained, so that the same amount of matter became spread over greater and greater distances. Yet even these almost empty regions are not absolute nothing. They may still contain thin gas, faint radiation, dark matter, magnetic traces, and particles passing through with almost no chance of meeting anything. That is what makes them so strange. They are not voids in the philosophical sense, but physical places where existence is stretched nearly to silence. If a spacecraft crossed one, it would not hit a wall of darkness or enter a magical nothingness. It would pass through an immense quiet where stars are rare, galaxies are distant, and the chance of encountering ordinary matter is unbelievably low. This teaches a powerful lesson about the universe. Emptiness is not a mistake, but a result of cosmic history. The same gravity that gathers galaxies also leaves behind regions where almost nothing gathers at all. Creation and absence are linked. Structure makes emptiness more visible, and emptiness gives structure its shape. So when you imagine the nearly empty parts of space, do not picture a blank gap with no meaning. Picture the long after effect of billions of years of cosmic sorting, where matter chose the pull of distant, crowded places, and what remained was a deep, patient quiet. Not nothing, but the closest the universe often comes to leaving a place untouched. How stars are born inside giant clouds. A star is born not from fire, but from cold darkness learning how to fall inward. Deep inside giant molecular clouds, where temperatures are low and dust blocks much of the outside starlight, huge amounts of hydrogen gas drift in a slow, shadowed calm. These clouds can be so enormous that they contain enough material to form thousands of stars. Yet most of the cloud may remain quiet for a long time, because gas does not collapse unless gravity gains the advantage over pressure, turbulence, and magnetic support. Then something disturbs the balance. A nearby supernova shockwave may pass through. A spiral arm of a galaxy may squeeze the cloud. Two clouds may collide, or turbulence inside the gas may create a dense pocket. In that pocket, matter gathers more tightly, and gravity begins its patient work. The denser the region becomes, the stronger its pull grows, and the more gas falls inward. As the collapsing core shrinks, it heats up at the center, not because it is burning yet, but because falling material is being compressed. Around it, leftover gas and dust often flatten into a rotating disk, because the material carries motion with it as it falls. From this disk, planets may one day form, but first the central object must become a star. In its early stage, it is called a protostar, still hidden inside the dusty cloud that made it. It may shoot narrow jets from its poles, clearing paths through the surrounding gas, as if the newborn star is carving its first tunnels out of the darkness. For a long time, it grows by feeding, pulling material from the disk and cloud around it. Only when the core becomes hot and dense enough for hydrogen fusion to begin does the true stellar life start. At that moment, the inward pull of gravity is balanced by the outward pressure created by nuclear energy, and the object becomes stable enough to shine for millions or billions of years. This is the quiet miracle of star formation. The universe does not light stars like lamps. It grows them inside cold clouds, through collapse, compression, rotation, and patience. The same dust that hides a newborn star also protects the conditions that allow it to form. The same darkness that looks empty from far away may be full of future suns. Why stars shine for millions or billions of years. A star survives for so long because it is locked in one of the most delicate balances in nature. Gravity trying to crush it inward, and its own inner heat pushing back outward. When a star first forms, gravity squeezes gas into a dense hot core, and if the core becomes hot enough, nuclear fusion begins. This does not mean the star is burning like wood or coal. A flame on Earth needs oxygen and chemical reactions. But a star shines because atomic nuclei deep in its center join together and release energy. That energy creates pressure, and pressure resists gravity. If gravity squeezes the core a little more, the core heats up and fusion increases, pushing back harder. If the star expands too much, the core cools slightly and fusion slows, allowing gravity to pull inward again. This self-correcting balance lets many stars remain stable for enormous stretches of time. They are not exploding every second, and they are not simply leaking light until they fade. They are living in a controlled tension, a long negotiation between collapse and release. The reason this can last millions or billions of years is that stars contain an immense amount of fuel, and fusion is extraordinarily efficient compared with ordinary burning. Even a tiny amount of matter converted into energy can produce a tremendous amount of light and heat. But the lifetime of a star depends strongly on its mass. A massive star has more fuel, but it burns through it much faster because its core is under greater pressure and runs fusion at a furious rate. Smaller stars use their fuel more slowly, glowing with patience rather than violence. And some can last far longer than the current age of the universe. This is why stars are not all cosmic candles with the same lifespan. Each one is a different balance of gravity, heat, fuel, and pressure. The light you see from a star is only the surface result of a deep inner struggle that has been going on for ages. Photons created in the core can take a very long time to work their way outward, bouncing through dense material before finally escaping into space. By the time that light reaches your eyes, it has already passed through layers of pressure, motion, and time. So when you look at a star, you are not seeing something simple. You are seeing a stable crisis, a sphere that keeps itself alive by almost collapsing and almost expanding, second after second, year after year, century after century. And perhaps that is the quiet lesson stars give. Endurance is not the absence of tension. Sometimes endurance is balance, the ability to hold opposing forces together long enough for darkness to become light. Hydrogen becomes light inside a star. Every beam of starlight begins as a struggle between particles that do not naturally want to touch. Inside a star's core, hydrogen is packed under extreme pressure and heat, not burning like fuel in a fire, but moving so violently that its nuclei are forced close together again and again. These hydrogen nuclei are positively charged, so they repel one another, like tiny magnets pushing apart before they can meet. Under ordinary conditions, they would never join. But in the heart of a star, gravity has created a furnace dense and hot enough for something remarkable to happen. Some hydrogen nuclei get close enough for the strong nuclear force to take over, binding them together and beginning the process of fusion. In stars like the Sun, this happens mainly through a chain of steps where hydrogen is gradually transformed into helium. Along the way, a small amount of mass is converted into energy. It is not much from any single reaction, but there are so many reactions happening inside a star that the total energy becomes enormous. This energy first appears as intense radiation in the core, far more energetic than the gentle sunlight that eventually reaches your skin. But it does not simply fly straight out. The star's interior is crowded, dense, and difficult to escape. Light particles are absorbed, scattered, and re-emitted countless times, wandering slowly through the star's layers in a journey that can take a very long time. Meanwhile, tiny particles called neutrinos escape almost immediately, passing through the star as if it were nearly transparent, carrying away a direct whisper from the core. The light, however, takes the long road. By the time energy finally reaches the surface, it has softened into the glow we recognize as starlight. From there, it travels freely through space, crossing millions of kilometers, then perhaps light years, until it reaches an eye, a telescope, a planet, or a quiet patch of dust. So when you feel sunlight on your face, you are not feeling simple warmth. You are receiving the final form of a process that began deep inside a star, where gravity pushed hydrogen into intimacy, where resistance became fusion, where matter gave up a fraction of itself and became radiance. This is how hydrogen becomes light, not by disappearing, but by transforming under pressure into something that can travel, warm, reveal, and make life possible. And perhaps that is the quiet wonder hidden inside every star. That light is not separate from matter, but matter learning how to shine. Why massive stars live fast and die young. The biggest stars die young because their own greatness forces them to spend themselves too quickly. A massive star is born with far more material than a star like the Sun. So at first, it seems as if it should live longer, like a larger candle with more wax. But stars do not work that way. The extra mass does not simply give the star more fuel. It crushes the core under stronger gravity, driving the temperature and pressure much higher. That intense core makes fusion happen at a far faster rate, and the star pours out energy with enormous power, shining thousands or even millions of times more brightly than smaller stars. It is wealthy, but it spends like a king who believes morning will never come. The more massive the star, the harder it must push outward to resist its own gravity, and that demand forces it to burn through its fuel with shocking speed. Some massive stars live only a few million years, while smaller, cooler stars can last for billions or even trillions of years. The difference is not just size, it is tempo. A low-mass star lives slowly, carefully, using its fuel with patience. A massive star lives in a state of extreme urgency, its core racing through stages of nuclear burning, building heavier elements in layers like a cosmic furnace with different shells. It also loses material through powerful stellar winds, throwing parts of itself into space even before its final collapse. And when the fuel in its core can no longer support the weight above it, gravity wins suddenly. The star's inner balance breaks, the core collapses, and the outer layers may explode outward as a supernova, scattering newly made elements into space. What remains may become a neutron star, or, if the core is massive enough, a black hole. This is why massive stars matter so deeply. They live briefly, but they change everything around them. They create many of the heavy elements that later become planets, minerals, oceans, and living bodies. They carve bubbles in surrounding gas with their radiation and winds. Their deaths can trigger the birth of new stars nearby. So a massive star is not a long-lasting lamp. It is a short-lived engine of transformation. It burns fast, dies violently, and leaves the universe richer than it found it. And perhaps that is the quiet lesson hidden in its life. Duration is not the only measure of importance. Some things exist briefly, but with such intensity that their ending becomes the beginning of countless others. How supernovae scatter elements into space. A supernova is not just a star dying. It is a star opening its locked vault and throwing the ingredients of future worlds into space. For most of its life, a massive star holds its elements inside layers, with lighter material near the outside and heavier material forged deeper within, closer to the crushing heat of the core. But when the star can no longer support itself, the inner balance fails with terrifying speed. The core collapses, and the outer layers are blasted outward in an explosion so bright it can briefly rival an entire galaxy. This explosion does more than create a beautiful flash. It tears open the star and sends its stored elements racing into the surrounding space at enormous speeds. Oxygen, carbon, silicon, sulfur, calcium, iron, and many other elements can be carried outward in expanding shells of gas, mixing with the thin material between stars. Some supernovae, especially the kind that happen when white dwarfs explode, are important sources of iron. Some heavier elements can also be made in violent, neutron-rich conditions, though scientists now know that events like neutron star collisions also play a major role for many of the heaviest elements. So the story is not as simple as saying every element comes from supernovae. The truth is more interesting. Supernovae are both forges and delivery systems. They create some elements, expose others that were made earlier inside the star, and scatter them into the galaxy, where they can become part of new gas clouds. Over time, those enriched clouds may collapse into new stars, and around those stars, dust grains can gather into planets, moons, rocks, and atmospheres. This is how a star's death becomes part of the universe's recycling process. Nothing about it is gentle in the moment. The shockwave is violent, the radiation is extreme. The star is destroyed as a star, yet from that destruction comes chemical possibility. Before many generations of stars lived and died, the universe had mostly simple ingredients. Supernovae helped change that, spreading complexity across space like ash from a cosmic fire. And perhaps that is why they feel so strangely beautiful. They remind you that creation is not always quiet and endings are not always empty. Sometimes, when a star dies, it does not disappear into meaninglessness. It gives away what it made in the dark, and the galaxy carries those gifts forward into things the star itself could never become. Why your body contains atoms made in ancient stars. Your body is not only alive on Earth, it is assembled from materials that the universe had to manufacture across billions of years. Every breath, every heartbeat, every thought depends on atoms with different cosmic histories. The hydrogen in your body is among the oldest material in existence, formed in the early universe long before stars or planets appeared. But the heavier elements that make life possible, carbon in your cells, oxygen in your blood, nitrogen in your DNA, calcium in your bones, phosphorus in your energy systems, iron in your hemoglobin, needed stars. They were not simply lying around from the beginning in useful amounts. Stars became the universe's chemical workshops, taking simple ingredients and transforming them through pressure, heat, and nuclear reactions into more complex elements. Some were made inside long-lived stars. Some were released by aging stars shedding their outer layers. Some were scattered by stellar explosions. Some of the heaviest atoms may have been forged in rare violent events such as neutron star collisions. This means your body is not from one star, one explosion, or one moment. It is a mixture of cosmic inheritances gathered from many ancient sources, recycled through gas clouds, folded into the sun's birth environment, trapped inside Earth, and eventually arranged into living chemistry. You are not made of stardust as a poetic exaggeration. You are made of atoms whose origins can be traced to real astrophysical processes. But the deeper wonder is not only that these atoms are old, it is that they became organized. Carbon did not know it would one day help build a cell. Oxygen did not know it would move through lungs. Iron did not know it would carry breath through blood. Matter passed through stars, space, clouds, rocks, oceans, and generations of life before becoming you. The universe did not create your body in a single act. It assembled the possibility of you slowly, across time, through chemistry, learning how to become biology. So when you look at your hands, you are not looking at something separate from the cosmos. You are looking at ancient material temporarily arranged into awareness. You are the universe's old atoms holding themselves together long enough to feel sunlight, ask questions, and remember where they came from. The quiet life cycle of a sun-like star. A sun-like star does not usually end with a scream. It spends most of its life in a long, steady silence, then leaves the universe like a lantern slowly uncovering its final glow. Its story begins inside a cold cloud, but unlike the most massive stars, it does not rush toward a violent fate. Once it becomes stable, a star like the Sun enters the longest and calmest part of its life, quietly turning hydrogen into helium in its core for billions of years. This stage is called the main sequence, and for a sun-like star, it is a deep middle age of balance where gravity pulls inward while heat and pressure push outward. For most of that time, from the outside, very little seems to change. Planets may orbit, light may fall on oceans, life may rise under its warmth, but inside the star is slowly changing its own center. Helium builds up in the core like ash from a fire that still burns around it. Eventually, the hydrogen fuel in the core becomes harder to use, and the balance begins to shift. The core contracts and heats, while the outer layers swell outward. The star becomes a red giant, larger, cooler at the surface. and far more luminous than before. This is not an explosion, but an aging process on a cosmic scale, as if the star is loosening its grip on the shape it held for so long. Later, it may begin fusing helium into carbon and oxygen in its core, creating new elements without the catastrophic violence of a supernova. But a sun-like star is not massive enough to keep building heavier and heavier elements forever. It reaches a limit. Its outer layers drift away into space, forming a glowing shell of gas called a planetary nebula, though it has nothing to do with planets. At the center, the exposed core remains as a white dwarf, small, dense, hot, and no longer producing energy through fusion. It shines only because it is still cooling from its former life. Over unimaginable time, it will fade more and more, becoming a dim remnant, a quiet ember of a star that once lit a system. This is the gentle life cycle of a sun-like star. Not brief, not explosive, but patient, transformative, and strangely tender. It gives light for billions of years, grows old, releases part of itself back into space, and leaves behind a compact memory of heat. And perhaps that is what makes stars like the sun so moving. Their greatness is not in dying violently, but in lasting long enough to make worlds possible, then fading with a calm that feels almost like wisdom. What will happen when the sun grows old? One day, the sun will still rise, but Earth will no longer be a world waiting for morning. The sun is about halfway through its long life, and for now it looks steady enough to feel eternal. But deep inside it, the balance is slowly changing. As hydrogen is used in the core and helium builds up, the sun gradually becomes brighter over time. This change is slow beyond human feeling, but it matters. Long before the sun becomes a red giant, its increasing brightness may warm Earth enough to damage the delicate systems that keep oceans stable. The planet could lose water to the atmosphere, then to space, and the blue world we know may become dry, hot, and unrecognizable while the sun still looks from a distance like an ordinary star. Much later, billions of years from now, the sun's core will contract while its outer layers swell outward, turning it into a red giant. Mercury and Venus will almost certainly be swallowed, and Earth's fate is less certain. It may be engulfed too, or it may survive only as a scorched, lifeless rock orbiting close to a swollen star that once made life possible. The sun will not explode as a supernova, because it is not massive enough for that kind of ending. Instead, it will lose its outer layers into space, creating a glowing shell of gas around the exposed core. That remaining core will become a white dwarf, small, dense, and hot, shining from leftover heat rather than new fusion. The solar system will become quieter, colder, and stranger, with planets and remnants orbiting a faded center. This future is not near enough to fear, but it is real enough to humble the mind. The same star that gave Earth warmth, weather, oceans, and life will eventually make Earth unable to remain what it is. And perhaps that is the deepest lesson of the aging sun. Even the things that protect us are temporary, not because they betray us, but because they too are part of time. The sun is not a permanent guardian. It is a long-burning chapter, and every sunrise is a brief gift from a star that is slowly spending itself. Why white dwarfs glow like stellar embers? A white dwarf glows because it is no longer alive as a star, yet it has not finished cooling from everything it once was. It is the exposed core left behind after a star like the sun sheds its outer layers, a dense remnant roughly the size of Earth, but holding a large fraction of a star's mass. What makes it strange is that it does not shine by making new energy through fusion. Its nuclear fire has ended. There is no steady furnace in its center, turning hydrogen into light. Instead, a white dwarf shines the way a hot coal glows after the flame has gone out. From stored heat, trapped inside matter packed so tightly that ordinary comparison almost fails. Its atoms are squeezed into an extreme state, and it is supported not by new burning, but by a quantum pressure that prevents the remnant from collapsing further unless it gains too much mass. At first, a young white dwarf can be incredibly hot, glowing white or blue-white, pouring leftover heat into space. But it cools very slowly because space is a poor thief of heat, and the remnant has so much thermal energy locked inside its dense body. Over billions of years, it fades from white to yellowish, then redder and dimmer, like an ember sinking deeper into ash. Some white dwarfs may even crystallize as they cool, their interiors forming a kind of stellar solid, like an ancient cosmic jewel cooling in silence. In the far future, if enough time passes, a white dwarf should become a black dwarf, cold, dark, and almost invisible. But the universe is not old enough for true black dwarfs to exist yet, because white dwarfs cool across timescales far longer than the current age of the cosmos. This means every white dwarf we observe is still glowing from a past life, still releasing the memory of a star that ended long ago. And there is something deeply quiet about that. A white dwarf does not rage, explode, or create new sunlight. It simply remains compact and patient, spending its last warmth across unimaginable time. So when you think of a white dwarf, do not picture a dead object with no story. Picture a stellar ember, a small dense memory of light, teaching that even after the fire has stopped, the heat of what once burned can linger almost forever. The strange fate of stars that burn out slowly. The strangest stars may be the ones that die so slowly the universe has not existed long enough to watch even one of them finish. These are the smallest, coolest stars, often called red dwarfs, and they live by a very different rhythm from brighter, heavier stars. A star like this uses its hydrogen with extraordinary patience. Because it is small, gravity does not crush its core with the same intensity found in massive stars, so fusion happens at a much gentler pace. Even more importantly, many red dwarfs are deeply mixed inside, meaning fresh hydrogen can keep circulating into the regions where fusion occurs, instead of leaving a large unused supply locked away. This makes them remarkably efficient. While a massive star spends its fuel in a short blaze and a sun-like star lives for billions of years, a red dwarf may shine for hundreds of billions or even trillions of years. That is so long that every red dwarf ever born is still young compared with its full lifetime. The universe is about 13.8 billion years old, which sounds ancient until you compare it with a star that may still be glowing when almost every bright star like the sun is gone. Their future is mostly theoretical, because no red dwarf has had time to reach old age yet. Models suggest that as some of these stars slowly use up their hydrogen, they may gradually become warmer and brighter for a time, perhaps shifting away from red toward a hotter blue-white phase, before eventually fading into a white dwarf made mostly of helium. Unlike heavier stars, they will not explode as supernovae. Many may never swell into dramatic red giants in the same way sun-like stars do. Their ending is not a cosmic scream, but a long, soft exhaustion, a quiet transformation from faint fire to dense remnant. This fate is strange because it reverses what your instincts expect. The smallest stars, the ones easiest to overlook, may be the last ordinary lights in the universe. Long after the most brilliant stars have burned out, long after many galaxies have aged into dimmer collections of remnants, these modest red stars could continue shining, not beautifully bright, but stubbornly present. And perhaps that is their lesson. The universe does not give endurance only to what is grand. Sometimes the faintest lights last the longest, carrying warmth through ages so vast that even the death of stars begins to feel less like an ending and more like an extremely slow forgetting. How black holes bend space and time. A black hole does not bend space and time because it is a monster in the dark. It bends them because gravity is what space-time does when mass becomes extreme. In everyday life, gravity feels like a pull, as if Earth is reaching upward and holding your feet to the ground. But Einstein's deeper idea was stranger and more elegant. Massive objects change the shape of space-time itself, and other objects move along those changed paths. A planet curves space-time gently. A star curves it more strongly. A black hole curves it so intensely that the usual geometry of the universe becomes almost unrecognizable near it. Space around it is not simply empty distance anymore. It is tilted, warped, and guided inward. Time is affected too. A clock closer to a strong gravitational field ticks more slowly compared with a clock far away. Near a black hole, this effect can become dramatic, not because time is broken, but because gravity changes the way time passes relative to different observers. Light is also forced to follow the curved shape of space-time, which is why black holes can act like cosmic lenses. They can bend and distort light from stars and galaxies behind them, stretching images into rings, arcs, or strange duplicated shapes. Sometimes the light from hot gas circling a black hole appears warped, with parts of the disk bent upward or around the darkness, not because the gas is painted that way, but because the path of light itself has been reshaped before reaching us. This is how something invisible can still reveal its presence. Not by shining, but by changing the routes of everything nearby. A black hole is not just an object inside space. It is a region where space and time have been curved into an extreme condition by collapsed mass. And that should make you question the quiet floor of reality beneath you. The universe is not a fixed stage with things moving across it. The stage can bend, the distance between events can be altered. The rhythm of time can change depending on where you are. Around a black hole, this truth becomes impossible to ignore. It shows that gravity is not merely a force pulling through space, but a deep rewriting of space and time themselves. So when you imagine a black hole, do not picture only a dark sphere. Picture the surrounding universe leaning inward, light changing direction, clocks disagreeing, and reality revealing that even the invisible shape of space-time can become one of the most powerful things in existence. Why black holes are not cosmic vacuum cleaners. A black hole does not hunt the universe. It only waits for matter foolish enough to come too close. The popular image makes it seem like a cosmic vacuum cleaner, sweeping up stars, planets, gas, and light from every direction with unstoppable hunger. But that is not how gravity works. A black hole's pull depends on its mass and your distance from it, just like the gravity of any other object. If the sun could somehow be replaced by a black hole with the exact same mass, Earth would not instantly spiral into darkness. It would continue orbiting almost as before, because the gravitational pull at Earth's distance would be essentially the same. The real danger begins only when something gets very close, near the region where escape becomes impossible. Far away, a black hole is not magical. It does not reach across the galaxy and drag everything inward. Stars can orbit black holes for millions or billions of years without falling in, just as planets orbit stars without automatically crashing into them. To actually be swallowed, matter must lose enough speed and angular momentum to fall inward instead of continuing around. That is why gas near a black hole often forms a swirling accretion disk. Not because the black hole is sucking it straight down like a drain, but because the gas is colliding, heating, shedding energy, and slowly spiraling closer. In fact, much of the matter near an active black hole may never fall in at all. Some of it can be flung away in powerful jets or heated so intensely that it shines across enormous distances. The black hole itself is dark, but the messy environment around it can become one of the brightest engines in the universe. This distinction matters because fear often comes from the wrong picture. A vacuum cleaner pulls because it creates a flow of air. Space has no such air current, and a black hole does not create a universal suction. It is a region of extremely strong gravity with a boundary that matters only if you cross it. Outside that boundary, the rules of motion still apply. You can orbit, you can pass by, you can escape if your path and speed allow it. So, a black hole is not a mouth devouring the cosmos. It is more like a gravitational cliff, invisible from far away, survivable at a distance, but final if you step past the edge. And perhaps that makes it even more interesting than the myth. The truth is not that black holes are monsters chasing everything. The truth is that they are patient extremes, waiting in the structure of space, revealing that the universe does not need evil to be dangerous. The event horizon, a boundary with no return. The event horizon is not a surface you can touch, but a line in reality after which every possible future points inward. From far away, it is tempting to imagine it as the black hole's skin, a dark shell wrapped around the place where gravity becomes absolute. But the truth is stranger. The event horizon is a boundary in space-time, not a physical wall. If you cross the horizon of a very large black hole, you might not feel anything special at that exact moment. There would be no glowing sign, no sudden impact, no hard edge under your feet. Locally, space might still seem like space. Your clock would still tick normally to you. Your thoughts would still feel like they belong to the present. But something deeper would have changed forever. Escape would no longer be one of the paths available to you. Outside the event horizon, a rocket with enough power could, in principle, move away. Light could still climb outward. Signals could still return to the wider universe. Inside it, even light cannot find a route back out, not because it becomes weak, but because the geometry of space-time has turned every outward direction into a path that still leads deeper inward. The future becomes narrowed. The black hole is no longer something in front of you. It is something your timeline must approach. To an outside observer watching you fall, your image would appear to slow and redden near the horizon, fading as your light struggles to escape. But from your own perspective, you would cross in finite time, unaware of any cosmic pause. This difference is part of what makes the event horizon so unsettling. It separates not only places but stories. On one side, events can still communicate with the universe. On the other, they become permanently private, sealed away from every distant eye. We do not know exactly what happens at the deepest center, where our current theories fail. But the horizon itself is already enough to disturb the mind. It is a boundary made from cause and effect, a point where information can enter but cannot return in any ordinary way. And perhaps that is why it feels so haunting. Most borders in life can be crossed twice. Doors can open, roads can be walked backward, mistakes can sometimes be repaired. But the event horizon is the universe's purest no-return line, a place where the map does not end, but the possibility of coming back does. So when you imagine it, do not picture a monster's mouth or a cosmic drain. Picture a quiet boundary where the future changes direction, where light loses its exits, and where reality teaches one of its coldest lessons. Not every threshold announces itself before it becomes irreversible. Why light cannot escape a black hole. Light cannot escape a black hole, not because it becomes tired, slow, or trapped like an insect in a jar, but because inside a black hole, the meaning of outward has been changed. Everywhere else in the universe, light moves at its natural speed, the fastest speed any signal can have. It does not need fuel, and it does not struggle the way a rocket struggles. If light leaves a lamp, a star, or a galaxy, it follows the shape of space-time in front of it, moving along the straightest path available. But near a black hole, space-time is curved so severely that those available paths begin to tilt inward. Outside the event horizon, light can still escape if it is aimed correctly. It may be bent, delayed, or reddened by gravity, but it still has routes that lead away. At the event horizon, the last outward paths disappear. Beyond that boundary, every possible direction light can take leads deeper into the black hole. This is the part that feels almost impossible. Light is still moving at light speed locally, but the structure it moves through no longer offers an exit. It is like trying to swim out of a river after the river itself has become a waterfall faster than any swimmer can climb. The photon is not weak. The future around it has been redirected. This is why a black hole looks black. It is not a dark object painted black, and it is not absorbing light like ordinary material. It is a region where emitted light cannot return to the outside universe. Anything that crosses the horizon can still exist, fall, change, and move, but it can no longer send news back. To distant observers, the black hole becomes a silence in the sky, surrounded perhaps by glowing gas, warped light, and violent heat, while the central region gives nothing back. And that is what makes it so haunting. Light is usually the universe's messenger. It tells us where stars are, what galaxies are made of, how hot something is, how fast it moves, and how far away it has traveled. But a black hole creates a place where the messenger loses all roads home. It does not defeat light by chasing it. It defeats light by changing the map. So when you imagine light falling into a black hole, do not picture a beam slowing down and fading from exhaustion. Picture reality bending so deeply inward that even the fastest thing in existence can only move toward a future it cannot report. How supermassive black holes live in galactic centers. At the heart of many galaxies sits a darkness so massive that the entire galaxy seems to arrange part of its history around it. These are supermassive black holes, objects with millions or even billions of times the mass of the Sun, usually found near the centers of large galaxies. Our own Milky Way has one called Sagittarius AI, a compact and powerful gravitational center surrounded by stars that whip around it at incredible speeds. But a supermassive black hole does not run a galaxy like a king controlling every citizen. Most stars in a galaxy are far too distant to feel it as the dominant force in their daily motion. The galaxy's overall gravity comes from all its stars, gas, dark matter, and structure combined. The black hole matters most in the crowded central region, where gas, dust, and stars pass close enough for its gravity to shape their paths. For long periods, a supermassive black hole may be almost quiet, feeding very little, hidden in the center like a sleeping engine. But when enough gas falls toward it, the material does not simply vanish at once. It forms a hot, rotating disk, heating through friction and compression until the region around the black hole can shine with astonishing brightness. In its active phase, the center of a galaxy can become an active galactic nucleus, and in extreme cases, a quasar, bright enough to be seen across enormous cosmic distances. Some of these systems also launch jets of particles far out into space, affecting the gas around the galaxy and sometimes slowing future star formation by heating or pushing material away. This means a supermassive black hole lives in cycles, quiet, feeding, blazing, influencing, then fading again when its fuel runs low. It is not alive in the biological sense, but it has a kind of cosmic metabolism, depending on what the galaxy delivers to its center. And that is what makes it so fascinating. A galaxy may look like a graceful city of stars, but deep in its core, there may be a hidden engine that occasionally wakes, shines without being a star, and changes the environment around it. So when you imagine a supermassive black hole in a galactic center, do not picture only a silent pit. Picture a sleeping heart of gravity, sometimes quiet for ages, sometimes bright enough to reveal itself across the universe, reminding you that even the darkest centers can shape the light around them. The mystery of how black holes grow so large. The strangest thing about supermassive black holes is not that they exist, but that some of them seem to have grown up before the universe was old enough to give them time. A black hole can gain mass in two main ways: by swallowing nearby gas and stars, and by merging with other black holes. That sounds simple until you look at the largest ones, especially the ancient quasars seen in the early universe, where black holes with millions or billions of solar masses already existed when cosmic history was still young. The mystery is how they became so enormous so quickly. If a black hole begins as the collapsed core of a massive star, it may start with only a few times the mass of the Sun. To reach supermassive size, it must feed extremely efficiently for a very long time, but feeding is not unlimited. As gas falls toward a black hole, it heats up and shines fiercely, and that radiation can push other gas away, slowing the meal. In other words, the black hole's own brightness can fight against its growth. This is why scientists look for other possibilities. Maybe some early black holes began much larger, forming when huge clouds of gas collapsed directly instead of first making ordinary stars. Maybe dense star clusters helped smaller black holes merge quickly. Maybe some black holes grew faster than expected during short, intense feeding phases, when thick flows of gas partly trapped their own radiation and allowed more material to fall inward. Galaxy mergers may also help by driving gas toward galactic centers, giving the central black hole a sudden feast. The answer may not be one single path, but several working together. Large seeds, rapid feeding, mergers, and special early universe conditions that made growth easier than it is today. And this is what makes the mystery so powerful. A supermassive black hole is not only an object, it is a fossil of cosmic history. Its size tells a story about how much gas reached the center, how often galaxies collided, how the first structures formed, and how quickly darkness could become enormous. So when you imagine one of these giants, do not picture only a black center inside a galaxy. Picture an ancient question still sitting there, heavy and silent. How did something that gives off no light become one of the brightest clues to the universe's earliest growth? What happens when black holes collide? When two black holes collide, the universe does not give you a crash of metal or a burst of ordinary flame. It gives you a silent rearrangement of gravity itself. Long before the final merger, the two black holes may orbit each other for millions of years, locked in a dark dance that slowly tightens. They do not have hard surfaces, so they do not smash like planets or stars. Instead, they circle closer and closer as the system loses energy. And the closer they get, the faster and more extreme the motion becomes. In the final moments, they can whip around each other at a significant fraction of the speed of light, twisting space-time with such violence that the event horizons distort, stretch, and finally become one. For a brief instant, the universe is dealing with something almost impossible to picture. Two separate regions of no return becoming a single larger one. The result is not simply the sum of both black holes. Some of the system's mass is converted into gravitational energy and sent outward as ripples through space-time, while the newly formed black hole shakes and settles into a stable shape, like a struck bell becoming quiet after its final note. If there is no surrounding gas, the merger may produce almost no light at all, meaning one of the most powerful events in existence can happen in complete darkness. We know these collisions occur because instruments on Earth can detect the tiny stretching and squeezing caused when those ripples pass through us, even after traveling across billions of years. This is what makes black hole collisions so haunting. They are not explosions you watch with your eyes, but events you feel through the geometry of reality. Two invisible objects meet, become one, and the universe remembers the impact by trembling. So when you imagine black holes colliding, do not picture a fiery impact in space. Picture darkness merging with darkness, mass becoming motion, motion becoming waves, and space-time itself carrying the news long after the collision is over. How gravitational waves ripple through space. A gravitational wave is what happens when space itself is disturbed, not like air shaking with sound, but like distance quietly stretching and squeezing as a message moves through the universe. To understand it, you have to let go of the idea that space is only a background where events happen. In Einstein's view, space and time form a flexible structure, and when massive objects move in extreme ways, they can send ripples through that structure. These ripples are gravitational waves. They are created most strongly by violent cosmic motions. Pairs of neutron stars spiraling together, black holes orbiting each other, or massive stellar cores collapsing in dramatic deaths. But the wave itself is not made of light, gas, or particles flying outward. It is a traveling change in the shape of space-time. As it passes through a region, it very slightly stretches space in one direction and compresses it in another, then reverses, again and again, with an effect so tiny that by the time it reaches Earth, it is almost unimaginably difficult to detect. You do not feel gravitational waves passing through your body. Your bones do not tremble. The ground does not roll like water. The change is far smaller than anything human senses can notice. Yet special observatories can measure it by using long laser beams and mirrors, watching for the faintest difference in distance as a wave passes through. This is how scientists first directly detected gravitational waves, not by seeing the event, but by measuring a tiny breathing motion in space itself. And that makes gravitational waves extraordinary. They give astronomy a new sense. For most of history, humans studied the universe mainly through light. Visible light, radio waves, X-rays, and other forms of radiation. But gravitational waves are different. They can carry news from events that may be dark, hidden, or difficult for light to escape from clearly. They let us listen to the motion of massive objects, to the final moments of cosmic collisions, to parts of the universe that do not speak in brightness. In a way, gravitational waves are not pictures of the cosmos. They are vibrations in its deepest grammar. They show that space is not perfectly still, and that time is not untouched by violence far away. Somewhere, two dense objects may circle and merge, and long after the light has faded or never appeared at all, the ripple can continue outward, crossing galaxies, passing through stars and planets, carrying the shape of an event across cosmic history. So when you hear that gravitational waves ripple through space, do not picture waves on water. Picture the measuring rods of reality changing for a moment, the universe itself carrying a memory of motion, and Earth receiving a whisper so faint that only patience, precision, and wonder could ever hear it. Why neutron stars are almost unimaginably dense. A neutron star is what happens when matter is pressed so hard that ordinary atoms can no longer remain themselves. After a massive star explodes, its core may collapse into an object only about the size of a city, yet holding more mass than the sun. That alone is almost impossible to picture. If Earth were squeezed to the density of a neutron star, it would not remain a planet in any familiar sense. It would become a tiny, terrifyingly compact remnant. The reason neutron stars are so dense is that gravity has crushed the core beyond the normal structure of matter. In everyday life, atoms are mostly empty space, with tiny nuclei surrounded by distant electrons. But inside a neutron star, that empty space is largely erased. Electrons and protons are forced together, forming neutrons, and the material becomes something closer to one enormous atomic nucleus than to any normal substance. A single spoonful of neutron star matter would weigh billions of tons on Earth, not because it is made of exotic magic, but because so much mass is packed into such a small volume. The surface gravity would be extreme. The pressure inside would be beyond anything found in planets or ordinary stars. The crust may be made of strange crystalline nuclear material, while deeper layers could contain forms of matter we still do not fully understand. Some scientists think the inner core might include even more unusual particles, perhaps matter squeezed into states that cannot exist anywhere else naturally. This is why neutron stars are not just dead star remnants. They are cosmic laboratories, places where nature tests physics under conditions no human machine can reproduce. They spin rapidly, carry powerful magnetic fields, and in some cases send beams of radiation into space like lighthouses. But beneath all that motion and signal lies the central truth. A neutron star is density taken almost to its limit before collapse becomes a black hole. It is matter refusing, for a time, to vanish behind an event horizon. And perhaps that is what makes it so haunting. A neutron star is not large like a galaxy, not bright like a young massive star, not empty like deep space. Its terror is concentration. It shows that the universe does not need size to be overwhelming. Sometimes the most extreme places are small, silent, and unimaginably heavy, holding the remains of a star, in a body so dense that the word solid no longer feels strong enough. The strange beauty of pulsars. A pulsar is a dead star that keeps time more precisely than almost anything nature has ever made. At first that sounds impossible, because a dead star should seem quiet, cold, and finished. But a pulsar is not an ordinary remnant. It is a rapidly spinning neutron star with an intense magnetic field, and when its magnetic poles are not perfectly lined up with its rotation, beams of radiation sweep through space like the light from a cosmic lighthouse. If one of those beams crosses Earth, our telescopes detect a pulse. Flash, silence, flash, silence, again and again, with astonishing regularity. Some pulsars rotate once every few seconds. Others spin many times in a single second, so fast that the idea of a star turning becomes almost unreal. What makes them beautiful is not softness, but order born from violence. A pulsar begins after a massive star collapses, leaving behind a compact core that spins faster as it shrinks, the same way a figure skater spins faster when pulling their arms inward. Its magnetic field becomes enormously strong, and charged particles are accelerated along invisible magnetic paths, producing radiation that can be seen in radio waves, X-rays, or even gamma rays. The pulsars are not the star turning on and off. The star is constantly emitting beams. We only see the beam when its sweep points toward us. This simple difference matters because it turns a terrifying object into a clock. Pulsars are so regular that scientists use them to test gravity, study the space between stars, search for planets around dead stars, and even detect tiny changes caused by gravitational waves passing through the galaxy. Some pulsars slow down gradually as they lose energy, while others suddenly glitch, spinning a little faster for reasons connected to changes inside the star. They are not perfect machines, but they are close enough to make the universe feel strangely mathematical without needing symbols. And there is something haunting in their discovery. The first pulsar signals were so regular that they were jokingly nicknamed as if they might be messages from another civilization. They were not alien voices. They were nature, speaking with a precision no one expected from the remains of a star. So when you think of a pulsar, do not imagine only a violent corpse in space. Imagine a lighthouse made from collapsed matter, spinning in darkness, sending its rhythm across hundreds or thousands of light years. How galaxies spin across billions of years. A galaxy can turn for billions of years without anyone pushing it, as if an entire city of stars has remembered a motion older than the stars themselves. This slow spin begins long before a galaxy becomes beautiful to look at. In the early universe, matter was not spread perfectly evenly. Gas, dark matter, and small clumps of material pulled on one another, drifted, collapsed, and merged. During that long gathering, tiny imbalances in motion became rotation. Once a cloud of cosmic material began to turn, it did not simply stop, because in space there is almost no friction acting on the whole galaxy, the way air slows a spinning wheel on Earth. As gravity drew matter inward, the rotation became more organized, and over time a galaxy could flatten into a disk, with stars, gas, and dust moving around a shared center. But a galaxy is not a solid wheel. The inner stars usually complete their orbits faster, while the outer regions take much longer, sometimes hundreds of millions of years for a single turn. Our Sun, for example, is moving around the center of the Milky Way, yet one full journey takes far longer than all of recorded human history. This means that when you look at a spiral galaxy, you are not seeing a frozen pattern. You are seeing motion stretched across timescales too vast for the human mind to feel directly. The stars do not stay locked inside the spiral arms like painted dots on a disk. Instead, many stars move through these arms, while the arms themselves are regions where gas can become compressed and new stars can form, making the pattern glow more clearly. This is why galaxy rotation is so strange. It is both orderly and restless. Everything is moving, but the motion is not obvious in a single photograph. A galaxy can look still only because we live too briefly to watch its turning. Its spin also reveals hidden structure. When astronomers measured how fast stars and gas move in the outer parts of galaxies, they found that visible matter alone could not easily explain the speeds. Something unseen appears to help hold these rotating systems together, shaping their motion from beyond what our eyes can detect. So the spin of a galaxy is not just a graceful dance, it is evidence. It tells us about the galaxy's birth, its mergers, its invisible mass, and the deep patience of gravity. And perhaps this is the most humbling part. While you sit still beneath the night sky, the Milky Way is carrying the Sun, Earth, and every sleeping city through a vast orbit around its center. Stillness is only a local feeling. On the scale of galaxies, everything you know is already in motion, turning with a structure so ancient that its first spin began before Earth had a name, before the Sun existed, before there was anyone here to look up and wonder why the stars seem so calm, why spiral galaxies look like cosmic storms. A spiral galaxy looks like a storm, but its arms are not clouds being blown by cosmic wind. They are vast lanes where gravity, gas, dust, and newborn stars make motion visible. When you see a spiral galaxy from far away, the shape can feel almost weather-like. A bright center, curved arms, dark streaks, glowing knots, and a sense that the whole thing is turning like a hurricane in deep space. But there is no atmosphere around a galaxy, no air pressure pushing the arms into shape, and no single storm system holding it together. The storm is a pattern made by gravity acting across enormous time. Inside a spiral galaxy, old stars often fill much of the disk with a softer yellowish light, while the spiral arms stand out because they contain more gas, dust, and young hot stars. These young stars shine blue-white and live relatively short lives, so they mark the places where star formation has happened recently. That is one reason spiral arms look so alive. They are not just decorations. They are stellar nurseries stretched across thousands of light years. Gas clouds drift into denser regions of the galactic disk, become compressed, cool, fragment, and form clusters of new stars. The brightest of these stars light up nearby gas, creating glowing nebulae, while dust blocks some starlight and forms dark lanes that twist along the arms like shadows in a storm. In many spiral galaxies, a central bar of stars can also help guide gas inward and reshape the arms, feeding waves of starbirth across the disk. Nearby galaxies can disturb the pattern too, pulling gently with gravity and stretching spiral structure into longer, looser, or more dramatic curves. This is why spiral galaxies look so dynamic, even though their changes unfold far too slowly for us to watch directly. The beauty you see is a long exposure of cosmic cause and effect. Gravity organizes the disk, gas responds, stars ignite, radiation carves glowing regions. Supernovae stir the surrounding material, and dust draws dark brushstrokes through the light. It is not chaos in the simple sense. It is organized unrest. A spiral galaxy looks like a storm because it contains turbulence, birth, heat, collapse, and motion. But it is also calmer and older than any storm on Earth could ever be. Its arms may last across many galactic rotations, changing gradually as material flows through them and new generations of stars appear. And that is what makes the image so powerful. You are not looking at a frozen pinwheel. You are looking at a living pattern of matter, where darkness and light cooperate to reveal structure. The bright knots are places where stars have recently formed. The dusty lanes are cold material waiting for gravity to gather it. The elegant curves are not painted onto space, but shaped by forces that have been working for billions of years. So when a spiral galaxy seems like a cosmic storm, it is because the universe has found a way to make gravity visible. Not as a formula, not as a command, but as a slow, luminous weather of stars. How elliptical galaxies became ancient star cities. An elliptical galaxy looks quiet because most of its storms happened long before you arrived to see the aftermath. Unlike spiral galaxies with bright arms, dark lanes, and obvious regions of fresh star birth, elliptical galaxies often appear smooth, rounded, and almost featureless, like enormous glowing cities whose fires have settled into an ancient haze. But that calm appearance hides a violent history. Many elliptical galaxies are thought to have formed through repeated mergers, when smaller galaxies passed through one another, pulled each other apart with gravity, and gradually blended their stars into a larger system. During these encounters, the neat disk structure of a spiral can be disturbed or destroyed. Stars are thrown into new paths, no longer orbiting mostly in a flat plane, but moving in many directions at once, creating a rounder or stretched shape. Gas may be compressed into bursts of star formation, used up quickly, heated until it cannot easily collapse, or pushed away by energetic processes near the galactic center. Over time, what remains is a galaxy rich in older stars and pour in the cold gas needed to make many new ones. This is why elliptical galaxies often shine with a warmer, reddish light. Not because they are literally red objects painted in space, but because many of their brightest young blue stars have already lived and died, leaving longer-lived older stars to dominate the glow. In large galaxy clusters, some giant ellipticals sit near the center like ancient capitals, surrounded by swarms of smaller galaxies and vast halos of hot gas. They can contain hundreds of billions or even trillions of stars, yet very little of the dramatic structure that makes spiral galaxies so visually sharp. Their beauty is not in arms or patterns, but in scale, age, and memory. They are stellar cities where the streets have been rearranged by past collisions, where the brightest youth has faded, and where most new construction has slowed. Yet they are not useless or empty. Elliptical galaxies help astronomers study how galaxies grow, how mergers shape cosmic structure, how star formation can shut down, and how enormous central black holes may influence their surroundings. They remind us that a galaxy's appearance is a record of its life. A spiral galaxy may show ongoing creation, but an elliptical galaxy often shows what remains after creation has mostly quieted. It is the difference between watching a city being built and walking through an old empire after its loudest centuries have passed. So when you see an elliptical galaxy, do not mistake smoothness for simplicity. You are looking at the softened face of ancient violence, a vast population of stars whose individual motions are hidden inside a single pale glow. A cosmic city so old that its chaos has had time to become silence. Why some galaxies are still forming stars? A galaxy can be ancient and still give birth, because star formation does not end when a galaxy becomes old. It ends when the galaxy loses the cold gas that can collapse into new suns. This is the key difference between a dead-looking galaxy and one that still feels alive. Stars are not made from empty space or from light itself. They form when huge clouds of gas, mostly hydrogen, become cold and dense enough for gravity to pull them inward. If the gas stays too hot, too spread out, or too violently stirred, it resists collapse and remains only a cloud. But when parts of it cool, gather, and fragment, small dense pockets appear, and inside those pockets, new stars begin. Some galaxies are still forming stars because they still carry large reservoirs of this usable gas, especially in their disks, outer regions, or disturbed clouds. Others keep receiving fresh gas from outside, slowly drawing it in from the thin material between galaxies, almost like a city still being supplied by distant roads. Galaxy interactions can also awaken star formation. When two galaxies pass near each other, they do not need to collide star against star. Their gravity can shake gas loose, compress clouds, and drive material into regions where new stars ignite in bursts. This is why some irregular galaxies and merging galaxies can glow with young blue stars and bright nebulae, as if the disturbance itself has pressed hidden fuel into flame. But star formation is not simply more gas equals more stars. Galaxies live inside a balance. New stars heat and stir their surroundings. Massive young stars release strong radiation, powerful winds, and later explode as supernovae, pushing gas outward and sometimes preventing nearby clouds from collapsing too quickly. This feedback can slow star birth, but it can also shape clouds into new dense edges where more stars may form. A galaxy that is still forming stars is therefore not peaceful in a simple way. It is regulated, restless, and supplied. It has enough cold material to create, enough gravity to gather, and not so much heating that all future birth is shut down. In contrast, galaxies that have mostly stopped forming stars may have used up their cold gas, lost it through winds, had it stripped away in crowded galaxy clusters, or seen it heated by energetic activity near their centers until it can no longer fall into star-making clouds. This means the life of a galaxy is not measured only by how many stars it already has, but by whether it still has the conditions to make more. And that should change the way you look at the night sky. Every bright young star in a star-forming galaxy is not just a point of light. It is evidence that somewhere, a cold cloud survived the violence around it long enough to collapse. It is proof that the universe is not only aging, fading, and cooling, but still building in certain places. Some galaxies have become museums of old stars. Others remain workshops, turning dark gas into fire, turning silence into structure, and reminding us that even on cosmic scales, creation depends on something fragile, the ability of matter to become cold enough, dense enough, and patient enough to begin again. How galaxies merge without usually colliding star to star. A galaxy merger sounds like a cosmic traffic accident, but the strangest part is that almost none of the stars usually hit each other. This feels impossible at first, because galaxies can contain hundreds of billions of stars, and when two of them pass into the same region of space, it seems natural to imagine a storm of stellar collisions. But galaxies are not packed like sand. They are more like enormous oceans of distance, with scattered islands of light. A star may be huge compared with a planet, but compared with the space between stars, it is incredibly small. If the Sun were reduced to a tiny dot, the nearest star would still be placed far away on the scale of a city or more. So when two galaxies merge, most stars simply pass between one another, missing by vast margins. What truly collides is not usually star against star, but gravity against structure, gas against gas, and motion against motion. The invisible gravitational fields of the galaxies pull on each other long before their stars overlap. Their shapes stretch, their disks warp. Long streams of stars can be pulled outward into tidal tails, like glowing threads torn from the edges of a cosmic fabric. Some stars are thrown into wider orbits, some are sent toward the center, and some may even be flung into intergalactic space, becoming lonely wanderers between galaxies. The gas behaves differently. Unlike stars, gas clouds can crash, compress, heat up, and lose energy. This means the gas in merging galaxies may pile into dense regions, sometimes triggering bursts of new star formation. In the center, material can be driven inward, feeding intense activity around compact central objects and lighting up the galaxy's core. Over hundreds of millions or even billions of years, the two original galaxies may lose their clean identities, their shapes gradually blending into one larger system. The process is slow, not like a sudden explosion, but like two enormous histories being rewritten by gravity. A merger can turn a neat spiral into a disturbed, irregular form, or eventually help build a smoother galaxy where old stars move in many different directions. Yet the stars themselves are mostly not destroyed by impact. They are reassigned by gravity. Their paths change, their neighborhoods change, their sky would change, but they usually survive the encounter. This is what makes galaxy mergers so quietly strange. The word collision suggests contact, but on cosmic scales, contact is rare and influences everything. Two galaxies can pass through each other, tear each other open, ignite new stars from compressed gas, reshape their centers, and still have almost every individual star avoid a direct crash. It teaches you something subtle about the universe. Violence does not always require touch. Sometimes gravity alone is enough to dismantle a structure, stretch it across darkness, and rebuild it into something entirely new. The Milky Way's slow journey through space. The Milky Way is not drifting through space like a lonely island. It is being carried through an invisible network of gravity, history, and motion that began long before Earth existed. When you stand under the night sky, the galaxy can feel like the fixed ceiling of reality, a pale river of stars stretched above you, calm and unmoving. But that stillness is an illusion created by human scale. The Milky Way is traveling, not toward a single simple destination, and not through space like a spaceship with an engine, but as part of a vast gravitational flow. It belongs to a small family of galaxies called the Local Group. And that family is moving within a larger cosmic neighborhood shaped by nearby clusters, empty regions, and huge concentrations of mass. The galaxy is not choosing its path. It is responding to the uneven structure of the universe around it. Gravity from distant matter gently influences motion over immense spans of time, while the expansion of the universe stretches the space between faraway galaxy groups. This creates a strange picture. The Milky Way is moving locally under gravity, yet the wider universe is also expanding around that motion. Astronomers can study this journey by looking at the positions and speeds of nearby galaxies, and by measuring a subtle pattern in the cosmic microwave background. The ancient radiation left from the early universe, that pattern helps reveal that our galaxy, together with its local companions, has a motion relative to the larger cosmic rest frame. In other words, even the Milky Way has a kind of velocity through the deep background of the universe. But this journey is slow only from the viewpoint of cosmic time. For human life, it is unimaginable. Entire civilizations rise and fall before the galaxy's position changes in any way our eyes could notice. Continents move, species vanish, stars are born and die, while the Milky Way continues along its broad path through the cosmic web. It passes through no empty stage because space itself is structured. Filaments of galaxies, vast voids, clusters, and superclusters all form a faint architecture that guides motion. The Milky Way is not outside this architecture, it is embedded in it, like a single glowing city traveling with other cities along dark roads made of gravity. And this should quietly change the way you think about home. Earth is not only spinning, not only orbiting the sun, and not only being carried around the galaxy. The whole galaxy is moving through a universe whose largest structures are still shaping its direction. Your sense of standing still is local, useful, and deeply human, but it is not the full truth. Beneath your feet is a planet. Around you is a star system. Around that is a galaxy. And that galaxy is on a slow journey through space so vast that motion becomes almost indistinguishable from destiny. Why Andromeda is coming toward us. Andromeda is coming toward us because the universe is not simply expanding everywhere, like a balloon pulling every galaxy away from every other galaxy. That is the part most people misunderstand. On the larger scales, distant galaxies usually appear to recede because the space between huge galaxy groups is stretching over time. But nearby galaxies can still be bound together by gravity, and when gravity wins locally, expansion does not tear them apart. Andromeda, also called M31, is the largest spiral galaxy near the Milky Way, sitting about 2.5 million light-years away. That sounds impossibly far, but on the scale of the universe, it is close enough for the two galaxies to feel each other's gravity across deep time. They are part of the same small cosmic family, the local group, along with the Triangulum galaxy and many smaller dwarf galaxies. Inside this family, gravity is stronger than the effect of cosmic expansion, so Andromeda is not breaking the expansion of the universe by moving toward us. It is simply close enough, massive enough, and gravitationally connected enough that its motion is shaped more by local attraction than by the stretching of distant space. We know Andromeda is approaching because its light is blue-shifted. When an object moves toward us, the waves of its light are slightly compressed, shifting them toward the blue side of the spectrum. This does not mean Andromeda looks bright blue in the sky to the naked eye. It means careful measurements reveal that its light carries the fingerprint of motion toward us. But Andromeda is not falling toward the Milky Way like a stone dropped straight down. Its path is shaped by many things. Its own motion from the early history of the local group, the pull of the Milky Way, the influence of dark matter halos surrounding both galaxies, and the gravitational presence of smaller galaxies nearby. In fact, when astronomers talk about Andromeda coming toward us, they are describing a long, complex orbital relationship, not a sudden attack. The two galaxies are massive systems moving through a shared gravitational environment, slowly changing each other's future over billions of years. The dark matter halos are especially important because they extend far beyond the visible stars. A galaxy is not only the glowing disk we photograph. It is surrounded by a much larger invisible halo that adds mass and helps shape motion. These halos can overlap and interact long before the bright star-filled parts come near each other, meaning the future encounter begins gravitationally before it becomes visually dramatic. Andromeda's approach also reveals something deeper about cosmic scale. The expansion of the universe is real. But it is not a simple wind blowing through every corner of space. Your body is not expanding. Earth is not expanding away from the moon. The solar system is not being pulled apart by expansion. The Milky Way and Andromeda are also close enough to be held inside a gravitational relationship. Expansion dominates where distances are enormous and objects are not strongly bound. Gravity dominates where matter has gathered into systems. This is why some galaxies flee from us while Andromeda approaches. The universe is not giving every galaxy the same instruction. It is a layered reality where local gravity and cosmic expansion coexist. And that makes Andromeda's motion more meaningful than a future collision headline. It is evidence that the night sky is not frozen. It is evidence that galaxies remember the conditions of their birth, that invisible mass shapes visible motion, and that even across millions of light years, gravity can turn separation into approach. When you look toward Andromeda, you are not just looking at another galaxy, you are looking at a neighbor already connected to our fate, a vast island of stars moving slowly through darkness, not because it chooses us, not because the universe is collapsing, but because on this scale, gravity has written a path stronger than distance. What the future collision with Andromeda may look like. The future collision with Andromeda will not look like the end of the sky at first. It will look like the night slowly learning a new shape. If Earth still had observers billions of years from now, Andromeda would no longer be a faint smudge barely visible under dark skies. It would grow larger, wider, and more detailed generation after generation, until its pale disk stretched across a huge part of the night, far brighter and more obvious than it is today. But this future is not a sudden impact, and it is not a scene of stars crashing like sparks in a fire. Galaxies are mostly empty space, so when the Milky Way and Andromeda finally begin passing through each other, most individual stars will miss one another by enormous distances. The real drama will come from gravity. The two galaxies will pull on each other, stretch each other, and distort each other's shapes. Their once separate disks may warp into long tidal streams, arcs of stars, and faint bridges of material drawn out across space. The sky from inside such a galaxy might become unfamiliar, with new star clouds, strange bands of light, and the glow of another galaxy no longer outside us, but mixed into our own. Gas clouds are far more likely to interact than stars. As they collide, compress, and cool, they could trigger waves of new star formation, creating bright blue clusters and glowing nebulae in places where the galaxy's material is stirred together. For a time, the merging system may look messy, luminous, and alive with fresh stellar birth, not because the stars are smashing, but because the raw material between them is being disturbed. The central black holes of both galaxies may eventually sink toward the shared center, influenced by surrounding stars and gas, and over a much longer time they could form a pair and perhaps merge, sending out gravitational waves. Yet even this is not instant. The entire event unfolds across hundreds of millions to billions of years, so slowly that no single human lifetime could watch it as motion. It would be more like living inside a cosmic time-lapse too slow for the body to notice. Our solar system would probably not be destroyed by a direct stellar collision, but its orbit around the new galactic center could change. It might be thrown into a wider region, pulled into a different path, or carried through a sky filled with new arrangements of stars. By then, the sun itself will be far older, and Earth may no longer be the comfortable world we know, which makes the Andromeda collision feel less like a disaster waiting for us, and more like a future chapter written for a universe that continues long after familiar life has changed. In the end, the Milky Way and Andromeda may settle into a larger, smoother galaxy, often imagined as an elliptical-like remnant, with the two old spirals no longer recognizable as separate star cities. Their bright arms may fade into a broader glow. Their histories may become blended. What once looked like two islands across darkness may become one vast stellar continent. And that is the strange beauty of this future collision. It is not destruction in the simple sense, but transformation on a scale almost too large to feel. The sky will not fall all at once. It will be rewritten slowly by gravity over ages, and somewhere in that far future, the Milky Way's familiar shape will become a memory. Not because it was shattered in an instant, but because the universe rarely keeps even its grandest structures unchanged forever. Why dwarf galaxies matter more than they look. Dwarf galaxies are the universe's small print, easy to overlook until you realize they may contain some of the clearest clues to how galaxies began. Beside giants like the Milky Way or Andromeda, a dwarf galaxy can seem almost insignificant, holding far fewer stars and often glowing so faintly that it hides against the darkness. Some contain billions of stars, while the smallest known examples may contain only thousands or tens of thousands of visible stars, making them look more like loose stellar fragments than true galaxies. But their importance is not measured by brightness alone. Dwarf galaxies matter because they are among the simplest galactic systems we can study, and simplicity can preserve history. Large galaxies have lived complicated lives. They have swallowed smaller systems, formed many generations of stars, stirred their gas, reshaped their disks, and buried old evidence under new activity. Dwarf galaxies, especially the faint ones orbiting larger galaxies, can act more like ancient records. Their stars often carry chemical fingerprints from earlier eras, showing what the universe was like when fewer heavy elements existed and star formation was more primitive. By studying the elements inside their old stars, astronomers can reconstruct how the first supernova enriched space, how quickly small galaxies formed, and how uneven early cosmic growth may have been. Dwarf galaxies also challenge the way we think about matter. Many of them appear to contain far more mass than their visible stars can explain, making them important places to study dark matter on smaller scales. In some ultra-faint dwarfs, the visible galaxy is only a thin sprinkle of stars inside a much larger gravitational structure. That means a dwarf galaxy may look fragile, but its hidden mass can be the reason it holds together at all. They also matter because larger galaxies are partly built from smaller ones. The Milky Way did not simply appear as a finished spiral. Over cosmic time, it grew by gathering gas and absorbing smaller systems, including dwarf galaxies. We can still see traces of this process in long streams of stars around the Milky Way, where a dwarf galaxy has been stretched apart by gravity and slowly dissolved into the larger halo. In this sense, dwarf galaxies are not just neighbors. They are leftovers, ingredients, and witnesses. Some are still forming stars in small, irregular bursts, while others lost their gas long ago and now contain mostly ancient stars. Some were shaped by nearby giants that stripped away their material, while others survived in relative isolation, keeping a quieter record of their own evolution. Their small size makes them vulnerable, but also revealing. A massive galaxy can hide its past under layers of later change, but a dwarf galaxy may show its scars more clearly. Missing gas, old star populations, strange shapes, or uneven star formation histories. They help scientists test whether our models of galaxy formation are correct. Because if we cannot explain the smallest galaxies, we may not fully understand the largest ones either. And this is the deeper lesson hidden in their faint light. The universe is not only explained by its grandest structures. Sometimes the smallest galaxies hold the oldest evidence, the strangest dark matter clues, and the unfinished stories of cosmic construction. A dwarf galaxy may look like a weak smudge beside a spiral giant, but inside that dimness can be a preserved chapter of the universe's youth. It reminds you that importance is not always bright, size is not always meaning, and some of the deepest truths in space may be written in systems so faint that humanity had to learn how to notice them at all. The hidden role of dark matter around galaxies. A galaxy's visible stars are only the lanterns. The larger structure holding the city together may be almost entirely unseen. This is the hidden role of dark matter around galaxies. Not to shine, not to form stars, not to glow in beautiful clouds, but to create a vast gravitational halo that shapes where ordinary matter can gather and how long a galaxy can remain stable. When you look at a galaxy, you mostly see stars, glowing gas, dusty lanes, and bright regions where new suns are forming. But that visible part may be only the central, luminous portion of a much larger system. Around many galaxies, scientists think there is an extended halo of dark matter, reaching far beyond the visible edge, like an invisible landscape surrounding a city of light. This halo does not behave like ordinary gas. It does not cool, clump, and collapse easily into stars. It does not form glowing disks or bright nebulae. Instead, it acts mainly through gravity, giving the galaxy extra mass that changes the motion of stars, gas, and smaller companion galaxies. Without this hidden mass, many galaxies would be difficult to explain as long-lived structures. Their outer stars and gas appear to move as if more matter is present than telescopes can see. And that missing gravitational influence is one of the strongest reasons dark matter became such a serious idea in astronomy. But its role goes deeper than simply holding galaxies together. Dark matter likely helped galaxies form in the first place. In the early universe, ordinary matter was still hot, energetic, and affected by radiation. But dark matter could begin gathering into invisible clumps under gravity. These clumps acted like gravitational wells. Later, ordinary gas fell into them, cooled, and eventually formed stars and galaxies. In this sense, a galaxy may not begin with light. It may begin with an invisible structure that teaches light where to collect. The bright galaxy is the part we can see, but the dark halo is part of the reason the bright galaxy exists at all. Dark matter also influences the shape and behavior of galactic neighborhoods. Small satellite galaxies can orbit inside a larger galaxy's dark matter halo, moving through a gravitational environment much bigger than the visible disk. Streams of stars torn from smaller galaxies may trace the shape of this hidden halo, leaving faint clues about its size and distribution. Gas entering a galaxy can also be guided by the halo's gravity, feeding future star formation or shaping the outer regions of the galaxy over long periods of time. Even galaxy mergers are affected by dark matter, because the invisible halos of galaxies can overlap and interact gravitationally before their bright stars come close. This means that when two galaxies approach each other, the first conversation between them may happen in darkness, through halos rather than through starlight. And yet dark matter remains profoundly mysterious. We do not directly see what it is made of. We know it is not simply ordinary dust, cold gas, or faint stars hiding from view, because those possibilities do not match the full pattern scientists observe. It seems to be something that interacts very weakly with light while still contributing gravity. That makes it both powerful and quiet, present in the architecture of galaxies, but absent from the images our eyes naturally trust. This should make you question what a galaxy really is. Is it the glowing disk in a telescope photograph? Or is that only the visible center of a larger invisible body? Is the Milky Way only its stars? Or is it also the dark halo surrounding it, extending far beyond the bright river we see in the night sky? Dark matter changes the answer. It suggests that galaxies are not just collections of stars, but luminous islands embedded in unseen gravitational oceans. The stars are the evidence we admire, but the hidden halo may be the framework that gave them a home. And perhaps that is the most unsettling part. The universe does not need to reveal its most important structures in light. Sometimes the thing that shapes everything is the thing that refuses to shine. Why dark matter does not shine. Dark matter does not shine because light seems to pass through its story without finding anything to hold on to. Ordinary matter becomes visible because it interacts with light in many ways. Stars shine because hot charged particles inside them produce radiation. Gas clouds glow when their atoms are energized. Dust becomes visible because it absorbs, blocks, or reflects starlight. Even something cold and dark, like a planet or a moon, can still be seen if light bounces from its surface. But dark matter appears to ignore this entire language of brightness. It does not seem to absorb light, reflect light, or emit light in any ordinary way. This is why it is called dark, not because it is a shadowy substance we have photographed, and not because it is simply hidden behind something else, But because it does not participate in the electromagnetic interactions that make ordinary matter visible, in simple terms, light is a form of electromagnetic radiation, and ordinary matter is full of charged particles that can respond to it. Electrons in atoms can absorb energy, release energy, and create the patterns of color that allow scientists to identify elements across space. Dark matter, as far as we can tell, does not have that kind of relationship with light. If it is made of particles, those particles likely have little or no electric charge, so photons do not easily grab them, bounce from them, or make them glow. This also explains why dark matter does not clump into bright stars, planets, or glowing clouds the way normal matter does. Ordinary gas can cool by releasing energy as light. When gas cools, it can collapse into denser structures, eventually forming stars. Dark matter cannot cool that way, at least not efficiently, because it does not easily radiate energy away. So instead of forming shining objects, it remains spread out in huge halos and gravitational structures, shaping galaxies from the outside and underneath without becoming part of the visible scenery. This makes dark matter deeply different from black dust, dead stars, or cold rocks. Those things are ordinary matter, and even if they are faint, they can still block, emit, reflect, or reveal light under the right conditions. Dark matter is stranger because its silence is not just weakness, it seems built into its nature. It is present through gravity, but absent from the direct conversation of light. Scientists infer it by watching what it does, not by seeing what it is. They study how galaxies rotate, how clusters of galaxies bend light from objects behind them, how the large-scale structure of the universe grew, and how visible matter moves as if guided by more mass than we can detect with telescopes. In that sense, dark matter is known by its fingerprints rather than its face. It is like hearing footsteps in a dark room, but never seeing the person who made them. And this is why the question of why it does not shine leads to something bigger. Our eyes evolved to trust light, and astronomy began as the study of things that glow. But dark matter teaches that visibility is not the same as existence. Something can shape the universe without becoming visible inside it. Something can help build galaxies without ever becoming a star. Something can outweigh the matter we know while refusing to appear in the colors our instruments are designed to catch. The fact that dark matter does not shine is not a small detail. It is the very reason it remained hidden for so long. The universe did not place its most important structures only where light could announce them. Some of its architecture may be written in gravity alone, in motion, in bending, in patterns, in the strange behavior of galaxies that seem to move as if surrounded by a silent mass. So when you think about dark matter, do not imagine a black fog floating between the stars. Imagine a substance that does not answer when light calls to it, yet still pulls on everything around it. It is not bright, not reflective, not glowing, and not visible in the usual sense. But in the quiet mathematics of motion, it speaks clearly enough to remind us that reality is not limited to what can shine. How we know. Dark matter exists without seeing it. We know dark matter is there because the visible universe keeps moving, as if it is being guided by something our telescopes cannot see. This is not a guess made from one strange observation, and it is not a story invented to make galaxies more mysterious. It comes from many different clues pointing in the same direction. One of the earliest clues came from galaxy clusters, where galaxies were moving so fast that the visible mass did not seem strong enough to hold the cluster together. If only the stars and glowing gas were present, many of those galaxies should have escaped long ago. Later, astronomers studied spiral galaxies and found another surprise. Stars and gas in the outer regions were orbiting too quickly compared with what the visible matter alone could explain. In a simple expectation, the farther stars should move much more slowly, because most of the visible mass is concentrated closer to the center. But in many galaxies, the outer regions move as though a large unseen halo of mass surrounds the visible disk. This does not prove by itself what dark matter is, but it strongly suggests that something with gravity is present beyond what shines. Another clue comes from gravitational lensing. where massive objects bend the light of more distant galaxies behind them. By studying how that background light is stretched, distorted, or multiplied, scientists can map where mass is, even when that mass gives off no light. Sometimes these maps show more mass than visible matter can account for, and sometimes the mass appears distributed in ways that do not match the glowing gas alone. One of the most famous examples is the Bullet Cluster, a collision between galaxy clusters where the hot ordinary gas was slowed and separated, while most of the gravitational mass appeared to pass through more easily. This matters because ordinary matter and dark matter seem to behave differently during such collisions. The gas, which we can detect in X-rays, interacts and piles up, while the unseen gravitational mass appears offset from it, as if the main mass is not the gas itself. Dark matter is also supported by the ancient light of the universe, the cosmic microwave background. Tiny patterns in that early radiation reveal how matter and energy were arranged when the universe was young, and those patterns fit much better if a large amount of non-shining matter was already helping structure grow. Then there is the large-scale arrangement of galaxies today, the cosmic web, with its filaments, clusters, and empty regions. Computer models that include dark matter do a far better job of producing a universe like the one we observe, where ordinary matter falls into invisible gravitational scaffolding and eventually forms galaxies. So the evidence is not one shadow on one wall. It is motion, bending light, cluster collisions, ancient radiation, and cosmic structure all telling a similar story. Still, honesty matters. Scientists have not yet directly identified the particle or substance that makes up dark matter. They know its gravitational effects with great confidence, but its true nature remains unknown. It might be a kind of particle beyond the ones we already understand, or something stranger that has not yet been captured by experiments. Some researchers also explore alternative ideas about gravity, asking whether our understanding of gravity could change on galactic scales. But the reason dark matter remains the leading explanation is that it connects many separate observations in one powerful framework. And that is what makes it so fascinating. We do not see dark matter the way we see a star, a nebula, or a planet. We see the universe behaving around it. We see galaxies rotating as if held by invisible weight. We see light bending around mass that is not fully luminous. We see galaxy clusters carrying a hidden gravitational map. We see the early universe carrying patterns that seem to require unseen matter before the first galaxies fully formed. It is a lesson in indirect knowledge. Not everything real announces itself directly. Sometimes you know something exists because everything around it refuses to make sense without it. Dark matter is not seen by the eye, but it is written into motion, structure, and the bending of light itself, reminding us that the universe can reveal an invisible presence not by showing its face, but by leaving its fingerprints everywhere. Why dark energy is stretching the universe faster. The universe is not only expanding. On the largest scales, it appears to be expanding with a kind of quiet acceleration that gravity alone was expected to resist. For a long time, the natural question seemed simple. After the Big Bang, would the expansion of the universe slow down forever, stop one day, or reverse into collapse? Gravity pulls matter together, so many scientists expected the expansion to be gradually losing strength, like a thrown object slowing as it rises. But in the late 1990s, observations of distant exploding stars changed the story. These stellar explosions, called Type Ia supernovae, can be used as cosmic distance markers because their brightness follows a useful pattern. When astronomers compared how bright they looked with how far away their host galaxies were, the result was startling. Distant supernovae appeared dimmer than expected. The most consistent explanation was that the expansion of the universe had not simply slowed over time. It had begun speeding up. Something was causing the large-scale stretching of space to accelerate. Scientists gave that unknown cause the name dark energy, but the name is more like a label for a mystery than a full explanation. Dark energy is not dark in the same way dark matter is dark. It is not known as invisible mass gathered around galaxies. It is more like a property of space itself, or something spread extremely smoothly through space, producing an effect that becomes more important as the universe grows larger. In everyday life, gravity wins easily. Your body does not expand. Earth does not pull away from the sun because of dark energy. Galaxies, star systems, and atoms remain bound because local forces are far stronger than this cosmic effect. But between galaxy groups that are not strongly tied together by gravity, space itself can stretch, and over enormous distances that stretching adds up. If dark energy stays constant, then as the universe expands and more space exists, the total influence of this strange component becomes larger in the cosmic story. Matter becomes more diluted as galaxies drift farther apart. But dark energy does not seem to thin out in the same simple way. That is why it can dominate the future. It does not push galaxies like a wind through space. It changes the behavior of space between distant structures. This is subtle but important. Galaxies are not mostly racing through a fixed emptiness. The distances between unbound galaxies are increasing because the fabric of the universe is expanding. Dark energy appears to make that expansion accelerate, meaning the most distant reachable galaxies may eventually slip beyond our future view, not because they vanish, but because their light will no longer be able to overcome the growing distance. And yet, for something so powerful, dark energy remains one of the least understood ideas in modern cosmology. It might be the energy of empty space, sometimes called a cosmological constant. It might be a field that changes over time. It might mean our understanding of gravity is incomplete on the largest scales. Scientists do not honestly know yet, and that uncertainty is part of what makes it so haunting. We can measure its effect, but we cannot yet say what it truly is. It is not a glowing substance, not a hidden ocean with waves we can touch, not a force you could feel in your hand. It is known through the fate of the universe itself. Dark energy matters because it turns cosmic history into a deeper question. The universe began hot and dense, formed atoms, stars, galaxies, clusters, and vast structures, yet its long-term future may be shaped by something that does not form objects at all. The grandest influence may not be a star, a black hole, or a galaxy, but an invisible tendency of space to stretch faster across the largest emptiness. So when you hear that dark energy is stretching the universe faster, do not imagine a giant hand pulling the cosmos apart. Picture every unbound distance becoming a little more difficult to cross, every far galaxy slowly becoming more isolated, every future observer seeing a smaller cosmic horizon than we can see today. It is a quiet acceleration, almost gentle in any single moment. But across billions of years it may decide what remains visible, what becomes unreachable, and how lonely the universe eventually becomes. The strange acceleration of cosmic expansion. The strangest part of cosmic acceleration is that no galaxy has to press a gas pedal for the universe to speed up. Nothing is flying through space with engines, and there is no explosion pushing galaxies outward from a central point. Cosmic expansion is stranger than motion through space. It is the stretching of space between distant, unbound galaxies. For much of the 20th century, scientists expected that this expansion should be slowing down. The reasons seem natural. Matter has gravity, and gravity attracts. Even if the universe began expanding, the combined pull of galaxies, gas, and dark matter should have acted like a brake, gradually weakening that expansion over time. The great mystery came when measurements suggested the opposite on the largest scales. The expansion had slowed in the early universe, but later began accelerating. This does not mean nearby galaxies, star systems, or planets are being torn apart. Bound structures still hold together. The acceleration becomes important across enormous distances, where galaxies are not tied strongly enough by local gravity to resist the stretching between them. To picture it correctly, do not imagine galaxies racing faster through a fixed, empty arena. Imagine the arena itself changing so that the distance between faraway regions grows faster with time. A distant galaxy can appear to recede, not because it is traveling through space like a rocket, but because more space is appearing between us and it as the universe evolves. The discovery was unsettling because it changed the emotional direction of cosmology. The future no longer looked like a simple contest where expansion gradually lost against gravity. Instead, the universe seemed to contain a hidden ingredient or property that becomes dominant as space grows emptier. Scientists often describe this using dark energy, but the honest truth is that the name does not solve the mystery. It only marks the place where our understanding is incomplete. The acceleration is measured through several clues working together. Distant supernovae that appear farther away than expected, patterns in the cosmic microwave background that reveal the early structure of the universe, and the large-scale distribution of galaxies that shows how cosmic expansion has changed over time. These clues do not show dark energy directly like a glowing object in a telescope. They show its effect in the history of distance itself. That is what makes it so different from ordinary discoveries. A new planet can be photographed. A new star can be measured by its light. But cosmic acceleration is discovered by comparing the universe at different ages and realizing that the expansion rate has not followed the path gravity alone would predict. The weirdness becomes even deeper when you consider that dark energy may not grow thinner, as space expands in the same way matter does. Matter becomes more spread out when the universe grows, like dust scattered through a larger room. Radiation stretches and loses energy, but if dark energy is connected to empty space itself, then every new stretch of space carries that same property with it. This would make the universe's emptiness more influential over time, not less. In the young universe, matter was dense enough to shape the story strongly. Galaxies formed, clusters grew, and gravity built structure from tiny early differences. But as expansion continued, matter became more diluted across cosmic distances, and the strange effect driving acceleration became more important. The universe slowly shifted from a structure-building era into an acceleration-dominated era. That shift is one of the most profound changes in cosmic history, because it means the largest scale future is not mainly controlled by the matter we can count in galaxies, but by something woven into the behavior of space itself. And still, scientists remain careful. Dark energy might be a constant property of space. It might change slowly over time. It might point to a deeper theory of gravity that we have not yet found. The fact that we can measure the acceleration more clearly than we can explain its cause is exactly what makes it scientifically powerful. It is a reminder that the universe can be precise without being fully understood. So when you hear that cosmic expansion is accelerating, do not picture chaos, speed, or galaxies being violently hurled away. Picture a silent change in the rules of distance, a slow widening of the cosmic map, a future in which the largest separations become harder and harder to bridge. The acceleration is not loud. It does not burn. It does not shine. But across billions of years, it may decide which galaxies remain visible, which regions become unreachable, and whether the universe grows into a colder, lonelier place where each cosmic island sees less and less of the whole. What redshift reveals about distant galaxies? Redshift is the quiet clue hidden inside galaxy light, revealing not only where a distant galaxy is, but how the universe has stretched while that light was traveling to us. When astronomers look at a faraway galaxy, they are not simply collecting brightness. They are reading a message that has crossed millions or billions of years. Inside that message are patterns, like fingerprints, created by atoms in stars and gas. Hydrogen, oxygen, calcium, and other elements leave recognizable marks in light, not as words, but as specific dark or bright lines in the spectrum. In a nearby laboratory, those lines appear at known positions. But in distant galaxies, the same lines are often shifted toward the redder side of the spectrum. This is called redshift. It does not usually mean the galaxy itself is actually red to the eye. And it does not mean the light became tired in a simple physical sense. It means the wavelength of the light has been stretched before reaching us. For many distant galaxies, the main reason is cosmic expansion. While the light was traveling, the space between us and that galaxy expanded, stretching the light along with it. The longer the journey, the more stretching can accumulate. So redshift becomes a kind of cosmic distance and time indicator. A galaxy with a larger redshift is usually being seen farther away and further back in cosmic history because its light left when the universe was younger. This is why redshift is so powerful. It turns light into a time machine with measurements. It allows astronomers to place galaxies in the story of the universe. Which ones are nearby and mature? Which ones are ancient and young-looking because we see them as they were long ago? And how the expansion of space has changed across cosmic time. Redshift also helps reveal motion, but carefully. Nearby objects can have redshift or blueshift because of their own local movement toward or away from us. But for extremely distant galaxies, the dominant effect is usually the stretching of space itself, not simply the galaxy flying through space like a rocket. This distinction matters because redshift is not just speed. It is a record of the changing scale of the universe. By comparing redshift with brightness, size, and structure, scientists can learn how galaxies evolved. When they formed many stars, when their growth slowed, how clusters developed, and how the large-scale web of galaxies took shape. Redshift can even move light beyond what human eyes can see. A galaxy whose ultraviolet light began as energetic radiation may have that light stretched into visible or infrared wavelengths by the time it reaches our telescopes. This is one reason infrared telescopes are so important for studying the early universe. They do not merely look at a different color, they recover ancient light that expansion has transformed during its journey. In this way, redshift teaches a deeply unsettling lesson. The universe is not just a place where light travels through distance. The distance itself changes while the light is on its way. A photon may leave a young galaxy when the cosmos is smaller, cross-expanding space for billions of years, and arrive carrying evidence of that expansion in its stretched wavelength. The light becomes a witness to the universe's growth. And because different galaxies show different redshifts, astronomers can build a three-dimensional and historical map of the cosmos, not only showing where galaxies are, but where they were in time. So when you hear that a galaxy is redshifted, do not imagine a simple color change. Imagine ancient light being pulled longer by the growth of space, carrying atomic fingerprints from a galaxy that may have changed completely by now. Imagine a signal that tells us distance, motion, age, chemistry, and cosmic history at once. Redshift is not loud, dramatic, or visible as a glowing sign in the sky. It is subtler than that. It is the universe leaving stretch marks on light, allowing us to read the expansion of reality itself in the faint glow of galaxies almost, too far away to touch with thought. Space becomes colder as the universe expands because the cosmos is not only growing larger, it is stretching the energy inside it thinner and quieter. In the earliest ages, the universe was not a dark, frozen emptiness. It was extremely hot, dense, and filled with radiation and particles packed so closely together that light could not travel freely for long. Everything was crowded, energetic, and constantly interacting. But as the universe expanded, the same amount of radiation and matter occupied a larger and larger volume. This changed the temperature of the cosmic background in two important ways. First, particles became more spread out, so they collided less often and shared energy less intensely. Second, and even more importantly, the light itself was stretched by the expansion of space. Light travels in waves, and when space expands while light is moving through it, those waves become longer. Longer wavelengths mean lower energy, and lower energy means colder radiation. This is why the cosmic microwave background, the leftover glow from the early universe, is now only a few degrees above absolute zero. It did not begin that cold. Long ago, it was hot enough to glow like the surface of a star-like fire filling all directions. Over billions of years, the expansion of space stretched that ancient light until it faded into microwaves, a cold whisper spread across the sky. This cooling is not the same as a cup of tea cooling on a table, where heat escapes into the surrounding air. The universe has no outside room for its heat to leak into. Instead, the cooling happens because expansion changes the conditions inside the universe itself. Distances grow, radiation stretches, matter thins out, and the average background temperature falls. But this does not mean every place in space is equally cold. or that everything cools at the same rate. Stars are still hot because gravity compresses gas and nuclear fusion releases energy. Planets can have warm surfaces because they receive starlight or hold internal heat. Gas clouds can be heated by supernovae, radiation, or falling into deep gravitational wells. Local objects can remain warm, bright, or violently energetic, even while the universe as a whole becomes colder. The cooling of the universe is a large-scale trend, not a simple freeze happening evenly everywhere. It is the background that cools, the vast emptiness between structures, the ancient radiation that fills space, the thin material drifting between galaxies. And this creates a strange contrast. The universe can still make stars in some places while its overall glow fades. It can still produce explosions, jets, and burning suns while its average temperature quietly drops. The expansion acts like a slow cosmic dimmer, not switching off every lamp at once, but gradually stretching the oldest light and spreading matter across larger distances. In the far future, if expansion continues, the background radiation will become even colder. Its wavelengths stretch so long that it becomes harder and harder to detect. The universe will not suddenly become cold. It will become cold by patience. Each age will carry less of the early heat. Each vast region between galaxies will feel emptier. Each ancient photon will be stretched a little further from the fire it came from. And this is what makes cosmic cooling so haunting. The universe began in a state where heat, light, and matter were almost inseparable, and now it is becoming a place of wider distances and quieter radiation. Coldness is not invading from outside. It is being created by expansion itself. So when you imagine space becoming colder, do not picture a freezer opening in the dark. Picture the first light of the universe being stretched across billions of years until its fire becomes a faint microwave afterglow. Picture matter drifting farther apart. Picture the cosmos slowly spending its original heat, not by losing it to somewhere else, but by diluting it into a growing sky. Why space becomes colder as the universe expands. Space becomes colder as the universe expands because the cosmos is not only growing larger, it is stretching the energy inside it thinner and quieter. In the earliest ages, the universe was not a dark, frozen emptiness. It was extremely hot, dense, and filled with radiation and particles packed so closely together that light could not travel freely for long. Everything was crowded, energetic, and constantly interacting. But as the universe expanded, the same amount of radiation and matter occupied a larger and larger volume. This changed the temperature of the cosmic background in two important ways. First, particles became more spread out, so they collided less often and shared energy less intensely. Second, and even more importantly, the light itself was stretched by the expansion of space. Light travels in waves, and when space expands while light is moving through it, those waves become longer. Longer wavelengths mean lower energy, and lower energy means colder radiation. This is why the cosmic microwave background, the leftover glow from the early universe, is now only a few degrees above absolute zero. It did not begin that cold. Long ago, it was hot enough to glow like the surface of a star-like fire filling all directions. Over billions of years, the expansion of space stretched that ancient light until it faded into microwaves, a cold whisper spread across the sky. This cooling is not the same as a cup of tea cooling on a table, where heat escapes into the surrounding air. The universe has no outside room for its heat to leak into. Instead, the cooling happens because expansion changes the conditions inside the universe itself. Distances grow, radiation stretches, matter thins out, and the average background temperature falls. The heat death of the universe. The heat death of the universe is terrifying because it does not arrive as fire, collapse, or explosion, but as the slow disappearance of difference itself. The name can be misleading because heat death does not mean the universe becomes hot and burns away. It means the universe eventually approaches a state where energy is spread so evenly that almost nothing useful can happen anymore. Every process depends on imbalance. A star shines because its core is hotter and denser than the space around it. A planet has weather because sunlight, rotation, oceans, land, and atmosphere create uneven temperatures and motion. Life exists because living things constantly borrow usable energy from their surroundings, turn it into order for a while, and release waste heat back into the world. Even a simple machine works only because energy can flow from one state to another. Heat death is the idea that, in the far future, those differences fade. Stars will not shine forever. Gas for new star formation will become rarer. The bright age of galaxies will slowly give way to a darker age of remnants, cooling objects, scattered particles, and enormous distances. The important point is not that energy disappears. In physics, energy is not simply destroyed. The problem is that energy can become unavailable for doing work. If everything is nearly the same temperature, if matter is too spread out, if there are no strong gradients left, then the universe may still contain energy, but it will lack the organized contrast needed to build new complexity. This is entropy, the tendency for usable, concentrated order to become more spread out and less able to drive change. You can think of it without equations. A hot cup of coffee cools in a room because its heat spreads into the surroundings. Once the coffee and the room reach the same temperature, the energy has not vanished, but it can no longer flow in a useful way between them. Heat death imagines this logic expanded to the scale of everything. Over immense time, the universe may become like a room where all the coffee has cooled, all the fires have faded, and every remaining difference has been softened almost completely. Gravity complicates the story because it can gather matter into stars, galaxies, and black holes, creating structure even as the universe ages. But gravity also helps set the stage for long-term exhaustion. Stars use fuel. Galaxies lose the easy ability to create new bright generations. And the overall expansion separates distant regions so strongly that less and less can interact. In this future, there may be no dramatic final moment when everything suddenly stops. The end may be more like a fading of possibilities. Fewer new stars, fewer fresh sources of heat, fewer places where matter gathers densely enough to ignite, fewer signals able to cross the widening darkness. Eventually, if current ideas are broadly correct, the universe trends toward a thin, cold, quiet condition where meaningful change becomes rare beyond comprehension. This is why heat death feels so unsettling. It is not death by violence, it is death by balance. It is the universe becoming too even, too diluted, too settled to keep producing the kinds of events that make it feel alive to us. And yet there is a strange honesty in it. Every candle burns by spending a difference. Every star shines by using an imbalance. Every thought in your mind depends on energy flowing through ordered structures for a brief moment in time. Heat death does not make the universe meaningless, but it reveals that meaning, motion, and memory belong to an age of usable contrast. We live during a rare bright interval, when stars still burn, planets still warm, atoms still gather into chemistry, and the universe still has enough unevenness to create stories. So when you hear the phrase heat death, do not imagine a cosmic furnace. Imagine the last gradients fading, the last useful fires losing their purpose, the last great differences dissolving into an almost perfect stillness. It is the possible future where the universe does not end by breaking, but by becoming too quiet to begin again. Why the last stars will eventually fade. The last stars will not go out because darkness defeats them, but because every star is a temporary agreement between gravity and fuel. A star shines only as long as it can keep converting light elements into heavier ones in its core, releasing energy that pushes outward while gravity presses inward. For a while, this balance can look almost eternal. A star may glow for millions, billions, or even trillions of years depending on its mass, and the smallest stars are so efficient that none of them have had time to finish their lives yet. But efficiency is not infinity. Every star has a limited supply of usable fuel, and every moment of shining spends a little of that supply. The largest stars burn through their fuel quickly and die in dramatic ways, while smaller stars consume theirs with extraordinary patience, but all of them are moving in the same direction, from usable hydrogen toward less useful leftovers. The reason the last stars will fade is not only that individual stars age, but also that the universe will gradually lose the conditions needed to keep making new ones. Stars form from cold, dense gas clouds, and over cosmic time that gas is changed, scattered, heated, locked inside old stars, blown away by stellar winds, or trapped in remnants. Galaxies may recycle some material for a while, because dying stars return gas to space, and gravity can gather it again into new clouds. But recycling is never perfect. Some matter becomes locked in white dwarfs, neutron stars, black holes, planets and cold fragments. Some gas is pushed into places where it is too thin or too hot to collapse easily. Some galaxies stop forming many stars because their cold fuel has been used up or removed. Slowly, the universe moves from an age of abundant starbirth into an age where new stars become rare accidents. The final stars are likely to be small, faint, long-lived red dwarfs because they burn fuel slowly and can keep shining long after brighter stars have vanished. They will be the patient lamps of the far future, glowing weakly in galaxies that no longer look young or rich with blue star-forming regions. But even they are not permanent. Over immense spans of time, their hydrogen will be exhausted. Their fusion will weaken and end. What remains will no longer be a true star in the living sense, but a cooling remnant, giving off leftover heat rather than producing fresh energy in its core. The universe will still contain objects, but fewer of them will shine by their own power. This is an important distinction. Fading does not mean matter disappears. The atoms remain, the remnants remain, gravity remains. But the ability to turn fuel into steady starlight becomes rarer and rarer until it effectively ends. A star is not just a ball of matter, it is matter in the right condition to keep a fire balanced against collapse. Once those conditions vanish, the light cannot be maintained by memory alone. In the far future, there may still be rare events that briefly create light. Collisions, mergers, matter falling into compact objects, or unusual encounters between old remnants. But these would be scattered sparks, not a new age of stars. The great stellar era would be over. The sky would not go black in one moment. It would thin, dim, and age. Galaxies would lose their bright young populations. The blue lights would vanish first, then the sunlight lights, and finally the faint red stars would finish their long, quiet work. What makes this future so haunting is that stars feel like the universe's most natural expression of life and energy. They are the furnaces that made many elements, the anchors of planets, the clocks of galaxies, the lights by which worlds become visible. Yet they are also temporary. Every star is a countdown disguised as a glow. Its beauty comes from the fact that it is spending itself. So when you imagine the last stars fading, do not picture a switch being turned off across the cosmos. Picture a final generation of small red lights burning with almost unimaginable patience, separated by vast darkness, each one slowly using the last of its fuel until even the longest-lived fires can no longer continue. The universe will not forget stars because they were unimportant. It will lose them because even the most patient light has a source, and every source, given enough time, can run dry. The era of black holes in the far future. In the far future, the brightest objects may be gone, and the universe's most important landmarks may be the things that were once famous for not letting light escape. This is the black hole era, a possible age so distant that ordinary stars have faded. Fresh star formation has nearly ended, and the glowing architecture of galaxies has become a much quieter collection of remnants. By then, the universe would not be empty in the simple sense. It would still contain black holes, cold stellar corpses, scattered planets, faint particles, and enormous regions of expanding darkness. But black holes would become especially important because they are among the longest-lasting objects nature can make. A small star can burn for trillions of years, but a black hole, especially a supermassive one, can survive for time so vast that human language almost fails to hold them. During this era, black holes would no longer sit inside bright, active galaxies the way some do today. There would be little fresh gas left to feed them, and without surrounding material falling in, most would become almost perfectly silent. A black hole only looks dramatic when matter near it is heated, torn, and made to glow before crossing the horizon. Without that nearby fuel, the black hole itself gives almost nothing obvious to the sky. It would remain as a deep gravitational presence, a dark center surrounded by fewer and fewer things able to announce it. Over immense time, some black holes may still grow through rare mergers, or by swallowing objects that wander too close. A dead star remnant might be captured. A planet-sized body might drift inward. Two black holes might slowly spiral together after ages of gravitational influence. But these events would become sparse, separated by stretches of time, longer than the entire current age of the universe many times over. The black hole era is not an age of constant violence. It is an age of rare events inside a universe that has mostly run out of easy fuel. And yet, black holes are not truly eternal in our best current understanding. According to Stephen Hawking's work, black holes should very slowly lose energy through a process now called Hawking radiation. This radiation would be incredibly weak for large black holes, so weak that we cannot detect it from ordinary astrophysical black holes today. A large black hole is colder than the background radiation that currently fills space, so for now it absorbs more energy than it loses. But in the far future, as the universe keeps expanding and the background becomes colder and thinner, black holes would eventually lose more than they gain. They would begin the longest fading process imaginable. The smaller ones would evaporate first, while the largest supermassive black holes would persist for staggeringly long times. Their evaporation would not look like a normal fire burning out. It would be a slow leaking of energy from the edge of the possible, a faint process stretched across timescales so enormous that even galaxies would feel like brief sparks by comparison. Near the very end of a black hole's life, if the theory is correct, evaporation would become faster, and the final moment could release a last burst of energy. But for most of its existence, a black hole would not die dramatically. It would endure. That endurance is what makes the black hole era so haunting. The universe would have passed beyond the familiar age of shining stars, beyond the busy formation of new worlds, beyond the colorful youth of galaxies. What remains would be dominated by objects defined by absence, gravity, and patience. Black holes would become the last great vaults of mass, the last deep wells in a cosmos where ordinary light has mostly stopped renewing itself. They would carry the memory of everything that fell into them, not in a simple readable way, but as part of their mass, spin, and hidden history. A supermassive black hole in that future might be the final remnant of an entire galaxy's central life, long after its stars have cooled and its spiral or elliptical form has lost meaning. And this should make you question what it means for something to remain. A star remains by shining. A planet remains by orbiting. A galaxy remains by holding a population of stars. But a black hole remains differently. It remains by not releasing, by holding shape through gravity, by outlasting almost every luminous structure that once made the universe feel alive. The black hole era would be a time when the cosmos is not yet finished, but has become almost unreadable to eyes built for starlight. The great drama would not be bright creation, but slow endurance, followed by even slower disappearance. So when you imagine the far future ruled by black holes, do not imagine a crowded sky full of monsters. Imagine a nearly silent universe where the last massive shadows sit in widening darkness, rarely meeting, barely feeding, and slowly giving themselves back to the void through a whisper of radiation. It is an age where the strongest prisons in nature become the last remaining clocks, counting down not in seconds, not in years, but in spans of time so immense that even darkness itself begins to feel temporary. The final quiet darkness of the universe. The final quiet darkness of the universe may not be an empty nothing, but something even stranger, a reality where almost everything that could happen has already happened. This is not a sudden ending, not a cosmic curtain falling, and not a final explosion that closes the story with violence. It is the possible far future that comes after stars have faded, after galaxies have lost their familiar glow, after black holes have spent unimaginable ages slowly evaporating. If our current understanding of physics is correct, what remains would be a universe almost impossible to compare with the one we know. There may still be particles, faint radiation, stretched waves, and perhaps cold remnants depending on what matter ultimately does over extreme time. But the great engines of change would be gone or nearly gone. No bright stars would be forming new light. No warm planets would be circling young suns. No crowded galaxies would be building fresh generations of structure. The distances between unbound regions would have grown so vast that many parts of the universe would become permanently unreachable from one another. Light itself would be stretched to such long wavelengths that its energy would become almost meaningless by human standards. A faint trace of ancient events diluted across expanding space. This final darkness is quiet not because space is full of silence in the ordinary sense, but because there may be almost no organized activity left to create new signals. A signal needs a source. A source needs usable energy. Usable energy needs imbalance. And in this distant future, the universe may have smoothed away nearly every useful difference. There might still be gravity, quantum fields, and the laws of physics, but laws alone do not guarantee drama. A stage can remain after the actors are gone. This is what makes the idea so unsettling. The universe may not end by disappearing, but by becoming too spread out, too cold, and too exhausted to keep making stories. Even the word darkness is incomplete, because darkness usually means the absence of light in a place where light could still appear. But in this far future, light may no longer be waiting just beyond the horizon. The conditions that create sustained light may have vanished. The darkness would not be like night on Earth, where morning is hidden on the other side of the planet. It would be a darkness with no sunrise promised by rotation, no new stellar dawn arriving from a young cloud, no galaxy glowing nearby with fresh blue stars. If protons eventually decay, as some theories suggest, but experiments have not confirmed, even ordinary matter would slowly lose its familiar stability over immense time. If protons do not decay, some cold particles and remnants may persist far longer. But persistence is not the same as life, warmth, or renewal. Either way, the universe trends toward a state where recognizable structure becomes rarer and meaningful change becomes almost impossibly thin. The most haunting part is that this future would still be the universe. It would not be outside reality. It would not be a place where physics has stopped. It would be physics continuing after beauty, heat, stars, and complexity have mostly finished their work. The same laws that once allowed the first atoms to form, the first stars to ignite, the first galaxies to gather, and the first planets to cool, may also allow the final age to become nearly motionless. Creation and exhaustion are not separate universes. They are different chapters of the same one. And from our small moment inside the bright era, this should make the present feel almost impossible. We live while stars still shine, while elements still cycle, while planets can still be warmed, while chemistry can still build delicate forms, while memory and thought can briefly appear in a cosmos that will not always be so generous. The final quiet darkness does not make the universe meaningless. It makes this luminous interval more precious. It tells us that the night sky is not permanent scenery, but a temporary window in a much longer history. So when you think of the final darkness, do not picture nothingness. Picture a universe stretched beyond contact, filled with fading traces rather than bright events, where the last useful fires have gone out and the remaining particles drift through a silence older than all stars. It is not the universe screaming at the end. It is the universe whispering so softly that, eventually, there may be nothing left close enough to hear.